In the constellation Ursa Major, 13.4 billion light-years away, sits a galaxy that shouldn't exist. When its light began travelling toward Earth, the universe was barely 430 million years old, just 3% of its current age. This tiny smudge of ancient starlight has done something remarkable. It has forced astronomers to question decades of carefully constructed theories about how galaxies form, how black holes grow, and whether our understanding of cosmic evolution is fundamentally incomplete. This is GN-z11, and it breaks nearly every rule we thought we understood about the early universe. The galaxy's properties read like a list of impossibilities. It forms stars 20 times faster than the Milky Way despite being 25 times smaller. It harbours a supermassive black hole that had no time to grow to its current size. It shines with a luminosity that requires either an improbable number of young, massive stars or physics we haven't yet discovered. GN-z11 isn't just an outlier. It represents a fundamental challenge to the lambda cold dark matter model, the theoretical framework that has successfully explained cosmic structure for decades. The hunt for cosmic dawn. The Hubble Space Telescope launched in 1990 with a mission to peer deeper into space than any instrument before it. For astronomers, looking deeper into space means looking further back in time. Light from distant objects takes billions of years to reach Earth, so observing far galaxies means seeing the universe as it was when that light began its journey. By the early 2000s, Hubble had captured thousands of galaxies stretching across cosmic history, building a timeline of how these massive structures evolved. But there remained a critical gap in our understanding: the earliest epochs, when the first galaxies were just beginning to form. The period astronomers call the Dark Ages lasted from about 380,000 years after the Big Bang until roughly 200 million years later. During this time, the universe was filled with neutral hydrogen gas that absorbed most wavelengths of light, rendering the cosmos essentially opaque. No stars had formed yet. No galaxies existed. The universe was a dark, cooling cloud of primordial gas, gradually clumping under the influence of gravity. The end of this era, when the first stars ignited and began ionizing the surrounding hydrogen, is known as the epoch of Reionization. This transition marks one of the most important phases in cosmic history, yet we know remarkably little about it. Detecting galaxies from this early period presents enormous technical challenges. These objects are extraordinarily faint, having formed when the universe was a fraction of its current size. Their light has been stretched by cosmic expansion, shifting from ultraviolet wavelengths into the infrared spectrum. This redshift means that visible light telescopes cannot see them at all. Hubble's infrared capabilities extended its reach significantly, but even Hubble struggled to detect galaxies beyond a certain distance. When astronomers calculated the theoretical limit of Hubble's detection range, they estimated it might, at best, see galaxies from about 500 million years after the Big Bang. The Cosmic Assembly Near-Infrared Deep Extragalactic Legacy Survey, or CANDELS, represented Hubble's most ambitious attempt to map the early universe. Beginning in 2010, this multi-year program targeted several regions of the sky with exceptionally long exposure times, allowing Hubble to collect photons from extremely distant sources. One of these regions was the Great Observatory's Origins Deep Survey North Field, commonly called GOODS North. This patch of sky in the constellation Ursa Major had already been studied extensively by multiple telescopes, but Candle's observations would push the boundaries of what Hubble could detect. By 2015, Candles had produced stunning images showing thousands of galaxies at various distances and evolutionary stages. Most appeared as expected, their properties matching theoretical predictions about galaxy formation. Astronomers had developed sophisticated techniques for estimating galaxy distances based on their colors and brightness across different wavelengths. This photometric redshift method works because a galaxy's spectrum contains characteristic features that shift predictably with distance. By measuring how much these features have shifted, astronomers can calculate when the light was emitted. The technique works well for most galaxies, but it has limitations. Unusual objects, or those at extreme distances, can produce ambiguous results. Among the thousands of galaxies in the Good's North Field, one stood out. The object was faint, barely visible even in Hubble's deepest exposures, but its colours suggested something extraordinary. The photometric analysis indicated a redshift around 11, meaning the light had travelled for over 13 billion years. If correct, this galaxy formed when the universe was only 400 million years old, placing it right at the boundary of the epoch of Reionization. The object received a simple designation, GN-z11, combining its location in the GOODS North Field with an approximation of its redshift value. But simple designations often hide complex stories, and GN-z11's story was about to challenge everything astronomers thought they understood about early galaxy formation. The initial photometric measurements suggested GN-z11 was not only incredibly distant, but also surprisingly bright for such an early galaxy. Theoretical models predicted that galaxies from this epoch should be extremely faint, with low stellar masses and minimal star formation activity. Early galaxies were supposed to be small, dim building blocks that would gradually merge over billions of years to form the massive galaxies we see today. GN-z11 didn't fit this picture. Its luminosity exceeded expectations by a significant margin, suggesting either a remarkably efficient period of star formation or something more exotic. Astronomers needed better data to understand what they were seeing. Photometric redshifts, while useful for surveys of thousands of galaxies, carry substantial uncertainties. The only way to definitively confirm a galaxy's distance is through spectroscopy, which splits the light into its component wavelengths and searches for specific atomic emission lines. These lines act as cosmic barcodes, each element producing a unique pattern. By measuring how far these patterns have shifted toward longer wavelengths, astronomers can calculate the exact redshift. Spectroscopy is time-intensive, requiring hours of telescope time focused on a single target. But for an object like GN-z11, the investment was necessary. If its extreme distance could be confirmed, it would become the most distant galaxy ever observed spectroscopically. The breakthrough came in 2016 when a team led by Pascal Oesch used Hubble's Wide Field Camera, 3 in spectroscopic mode, to observe GN-z11. The instrument detected multiple emission lines in the galaxy's spectrum, allowing for a precise redshift measurement. The result was Z equals 11.1, confirming that GN-z11 existed just 400 million years after the Big Bang. This made it the most distant galaxy ever measured spectroscopically, shattering the previous record by about 150 million years. The discovery was published in the Astrophysical Journal in March 2016, marking a new milestone in observational astronomy. But the confirmation of GN-z11's distance was just the beginning. The real questions were about to emerge. When photons tell ancient stories. Understanding the concept of redshift is essential to comprehending why GN-z11's discovery matters so profoundly. When we observe distant objects in space, we aren't seeing them as they are now, but as they were when their light began travelling toward us. Light moves at a constant speed, 299,792 kilometers per second. But in an expanding universe, that light must traverse not only distance, but also expanding space itself. This expansion stretches the wavelengths of light, shifting them toward the red end of the spectrum. The further away an object is, the more its light has been redshifted. providing astronomers with a direct measurement of both distance and time. The relationship between redshift and distance isn't straightforward because the universe's expansion rate has changed over cosmic history. Early in the universe's life, expansion was slowing down due to the gravitational attraction of all the matter pulling everything together. Then, about 5 billion years ago, a mysterious force called dark energy began accelerating the expansion, causing galaxies to recede from each other at ever-increasing speeds. These changing expansion rates mean that a simple calculation won't convert redshift directly into distance. Astronomers must use cosmological models that account for dark matter, dark energy, and the universe's overall geometry to translate redshift measurements into meaningful cosmic timelines. GN-z11's redshift of 10.957 means that its light has been stretched by a factor of nearly 12. Wavelengths that were emitted in the ultraviolet part of the spectrum have been extended into the near-infrared, which is why Hubble's infrared camera was essential for detecting this galaxy. At the time GN-z11's light began its journey, the universe was only 430 million years old, compared to its current age of 13.8 billion years. The physical distance to GN-z11 is now approximately 32 billion light-years due to cosmic expansion. This might seem paradoxical. How can something be 32 billion light-years away in a universe that's only 13.8 billion years old? The answer lies in the fact that space itself has been expanding during those 13.4 billion years of travel time. When Hubble captured GN-z11 spectrum, the data revealed something unexpected. The galaxy showed strong emission lines from hydrogen and other elements, indicating active star formation. The intensity of these lines suggested that stars were forming at a rate of approximately 20 solar masses per year. For comparison, the Milky Way currently forms about 2 solar masses worth of new stars annually. This means GN-z11, despite being 25 times smaller than our galaxy, was producing stars 10 times faster per unit volume. Such vigorous star formation was not supposed to be possible so early in cosmic history. The spectrum also revealed information about GN-z11's chemical composition. When the universe emerged from the Big Bang, it consisted almost entirely of hydrogen and helium, with trace amounts of lithium. All heavier elements, carbon, oxygen, nitrogen, iron, and everything else, were forged inside stars through nuclear fusion. When massive stars explode as supernovae, they scatter these elements into space, enriching the gas that will form future generations of stars. This process takes time. The first stars, called population 3 stars, should have been composed of pure primordial gas with no heavy elements. Subsequent generations would show increasing amounts of these heavier elements, or metals as astronomers call them. GN-z11 spectrum showed clear evidence of heavy elements, particularly nitrogen, in surprisingly high abundances. This presented a timing problem. If GN-z11 formed just 430 million years after the Big Bang, there'd barely been enough time for even one generation of massive stars to live out their lives and explode, let alone enough cycles to build up the metal enrichment observed in the spectrum. The most massive stars burn through their fuel rapidly, living for only a few million years before going supernova. But even accounting for this, the enrichment levels in GN-z11 suggested an accelerated chemical evolution that current models struggled to explain. The galaxy's stellar mass provided another piece of the puzzle. Based on the spectrum and photometric data, astronomers estimated GN-z11 contained approximately 1 billion solar masses of stars. This might sound enormous, but it represents only about 1% of the Milky Way's stellar mass. However, GN-z11 achieved this mass in just a few hundred million years, while the Milky Way took over 13 billion years to reach its current size. The efficiency of star formation required to produce 1 billion solar masses in such a short time pushed the boundaries of what theoretical models considered feasible. Hubble's observations also provided estimates of GN-z11 size. The galaxy appeared remarkably compact, with a radius of only about 60 parsecs, or roughly 200 light-years. For comparison, the Milky Way's disk spans about 100,000 light-years. Packing 1 billion solar masses into such a small volume creates an extraordinarily dense stellar environment. The stellar density in GN-z11's core was comparable to that found in the centers of globular clusters, ancient spherical collections of stars that orbit galaxies. Some researchers speculated that GN-z11 might represent a massive globular cluster in formation, though this interpretation came with its own complications. The question of what powered GN-z11's remarkable luminosity became increasingly important. The simplest explanation was that the light came from young, massive stars. These stars burn extremely hot and bright, producing copious amounts of ultraviolet radiation. However, the number of such stars required to explain GN-z11's brightness seemed implausibly high. An alternative possibility was that some of the light came from an active galactic nucleus, a feeding supermassive black hole at the galaxy's center. This would have been surprising because supermassive black holes were thought to form over much longer timescales, requiring hundreds of millions of years to grow from stellar mass black holes through gradual accretion. The Hubble data couldn't definitively distinguish between these scenarios, leaving the mystery unsolved. These observations from Hubble established GN-z11 as an exceptional object, but they also raise more questions than they answered. How did this galaxy form so early? Where did its supernova-enriched gas come from? What process could sustain such intense star formation in the infant universe? The answers would have to wait for a more powerful telescope, one specifically designed to study the infrared universe where ancient galaxies reveal their secrets. That telescope was already under construction, preparing to revolutionize our understanding of cosmic dawn. Building a galaxy too quickly. The lambda cold dark matter model, usually abbreviated as lambda CDM, represents the current standard theory of cosmology. This framework successfully explains the large-scale structure of the universe, the cosmic microwave background radiation, and the observed acceleration of cosmic expansion. According to lambda CDM, galaxies form through a hierarchical process. Small dark matter halos collapse first, creating gravitational wells that attract ordinary matter. This matter cools and condenses, eventually forming stars. Over time, these small proto-galaxies merge and grow, gradually building the massive galaxies we see in the nearby universe. The process is bottom-up. Tiny structures merge to form progressively larger ones. This hierarchical formation has been extensively simulated using powerful computers that track the evolution of dark matter and gas across cosmic time. These simulations reproduce the overall structure of the universe remarkably well, generating realistic galaxy clusters, filaments and voids that match observations. However, the simulations also make specific predictions about when certain types of galaxies should appear and how massive they can become at different epochs. By 400 million years after the Big Bang, lambda CDM models predict that galaxies should be relatively small and faint. The universe was still in the process of forming its first substantial structures, and there simply hadn't been enough time for significant amounts of mass to accumulate. GN-z11 poses a direct challenge to these predictions. With 1 billion solar masses in stars, formed in only a few 100 million years, it represents an efficiency of galaxy assembly that seems impossible under standard hierarchical formation. To understand why, consider the timeline. The Big Bang occurs at time zero. For roughly 380,000 years, the universe is too hot for atoms to form. Once atoms form, the cosmic microwave background is released and the universe enters the dark ages. During this period, tiny density fluctuations left over from the early universe begin to grow under gravity's influence. These fluctuations eventually collapse into the first dark matter halos, which then attract gas. The first stars likely ignited around 100 to 200 million years after the Big Bang, though this timing remains uncertain. These population 3 stars were enormous, hundreds of times more massive than the Sun, and burn through their fuel in just a few million years. When they exploded as supernovae, they enriched the surrounding gas with the first heavy elements and possibly left behind stellar mass black holes. By 400 million years, according to lambda CDM, the universe should contain numerous small proto-galaxies, each hosting perhaps millions to tens of millions of solar masses in stars. These dwarf galaxies would gradually merge over the next several billion years to form larger structures. GN-z11 doesn't fit this picture. Its billion solar masses suggest either that it represents an unusually efficient merger of many smaller proto-galaxies, or that star formation occurred at rates far exceeding theoretical expectations. The merger scenario has problems. Gravitational dynamics govern how quickly galaxies can merge, and there are limits to how fast mass can be assembled. Even if every dark matter halo within a large region merged perfectly and converted all its gas into stars with perfect efficiency, both extremely optimistic assumptions, it would be difficult to produce something like GN-z11 by 430 million years. The star formation scenario has different problems. Stars form from cold molecular gas clouds that collapse under their own gravity. This process is limited by several physical mechanisms. As gas collapses and heats up, it radiates energy. But there's a limit to how fast cooling can occur. Additionally, once stars begin forming, they produce radiation and stellar winds that heat and disperse the surrounding gas, creating negative feedback that slows or stops further star formation. Supernova explosions add to this feedback by injecting tremendous amounts of energy into the interstellar medium. In massive galaxies today, these feedback processes are so efficient that only a small fraction of available gas actually forms stars. For GN-z11 to exist, something had to be different in the early universe. Perhaps feedback processes were less efficient, allowing gas to cool and form stars more readily. Perhaps dark matter halos grew more quickly than standard models predict. Or perhaps the initial conditions in this particular region of space were somehow special, leading to enhanced mass accumulation. Each possibility requires modifications to our standard picture of galaxy formation, but none provides a fully satisfactory explanation. The timing problem remains acute. There simply wasn't much time between the formation of the first stars and GN-z11's observed state. The galaxy's high star formation rate compounds the problem. Forming 20 solar masses of stars per year requires substantial amounts of cold gas. Where did this gas come from? In the standard picture, gas accretes onto dark matter halos through streams along cosmic filaments. But this accretion has a maximum rate determined by the halo's mass and the overall density of the universe at that epoch. GN-z11 star formation rate suggests it was accreting gas at or near the maximum possible rate, converting that gas into stars with remarkable efficiency, and somehow avoiding the feedback processes that normally shut down star formation in dense environments. The situation becomes even more puzzling when considering the galaxy's compact size. Packing so much stellar mass into such a small volume means GN-z11 had an extraordinarily high stellar density. This density resembles what we see in the cores of present-day massive galaxies, structures that took billions of years to assemble through mergers and violent relaxation. How did GN-z11 achieve this configuration so quickly? One possibility is that it formed through a rapid, intense starburst triggered by a major merger event. However, this just pushes the question back one step. What merged to create GN-z11? And how did those progenitors become massive enough to produce such a result? Some researchers have suggested that GN-z11 might not be a galaxy in the conventional sense at all, but rather a massive star cluster, or protoglobular cluster. This interpretation would explain the small size and high density, as globular clusters are naturally compact objects. However, GN-z11 is far more massive than typical globular clusters, which contain hundreds of thousands to a few million solar masses of stars. Additionally, this interpretation doesn't resolve the fundamental timing problem. Whether we call it a galaxy or a star cluster, the object contains a billion solar masses of stars that formed remarkably quickly. The discovery of GN-z11 forced theorists to re-examine their models of early galaxy formation. Some proposed that the initial conditions in certain regions of the early universe might have been more conducive to rapid structure formation. Perhaps these regions had higher than average densities or experienced less turbulence, allowing gas to cool and collapse more efficiently. Others suggested that our understanding of feedback processes in the early universe might be incomplete. Maybe supernova feedback was less effective at dispersing gas when the universe was denser and metallicity was lower. Or perhaps stellar radiation, rather than heating gas and preventing star formation, actually helped compress gas clouds and trigger more star formation under certain conditions. These theoretical adjustments could potentially explain individual galaxies, like GN-z11. But they raised a new question. How common were such objects? If GN-z11 was a rare outlier, perhaps representing an extremely unusual combination of circumstances, then the lambda CDM model could accommodate it without major revisions. The model predicts a range of outcomes and rare events do occur. But if galaxies like GN-z11 were common in the early universe, that would suggest something more fundamental was wrong with our understanding. The answer to this question would have to wait for the James Webb Space Telescope, which would survey the early universe with unprecedented sensitivity and reveal whether GN-z11 was alone or part of a population. The black hole that shouldn't exist. When the James Webb Space Telescope finally launched in December 2021, after decades of planning and numerous delays, it carried instruments specifically designed to study the infrared universe. Webb's primary mirror spans 6.5 meters in diameter, compared to Hubble's 2.4 meters, giving it substantially greater light collecting power. More importantly, Webb was optimized for infrared wavelengths, where redshifted light from ancient galaxies appears. The telescope's location at the L2 Lagrange point, about 1.5 million kilometers from Earth, placed it in a stable, cold environment ideal for infrared observations. Scientists had a long list of targets for Webb's first observations, and GN-z11 was near the top. In 2023, Webb's Near-Infrared Spectrograph, or NIRSPEC, captured a detailed spectrum of GN-z11. The data quality exceeded Hubble's observations by orders of magnitude, revealing spectral features that had been impossible to detect with previous instruments. The spectrum confirmed the galaxy's redshift and provided new information about its physical conditions. But it also revealed something unexpected: clear signatures of an actively accreting supermassive black hole at the galaxy's center. This discovery fundamentally changed the GN-z11 story and deepened the mystery surrounding this ancient galaxy. The evidence for the black hole came from multiple lines in the spectrum. First, astronomers detected highly ionized gas moving at extreme velocities, creating broad emission lines characteristic of material swirling around a black hole's accretion disk. Second, they found emission from doubly ionized helium and nitrogen ions in states that require extremely energetic ultraviolet photons to produce. photons more energetic than those typically generated by stars. Third, the spectrum showed evidence of gas at densities exceeding 1 billion particles per cubic centimetre, densities only found in the immediate vicinity of accreting black holes. Together, these signatures provided compelling evidence that GN-z11 hosted an active galactic nucleus, powered by a massive black hole. The black hole's mass was estimated at approximately 1.6 million times the mass of the Sun. This might not sound enormous compared to the supermassive black holes in nearby galaxies. The Milky Way's central black hole weighs 4 million solar masses, while the black hole in the giant elliptical galaxy M87 contains 6.5 billion solar masses. But GN-z11's black hole exists when the universe was only 430 million years old. This creates a severe timing problem. How did such a massive black hole form so quickly? The standard picture of black hole growth starts with stellar mass black holes, the remnants of massive stars that have exploded as supernovae. These black holes typically weigh 10 to 100 solar masses. They grow by accreting gas from their surroundings, gradually increasing in mass over time. However, there's a fundamental limit to how fast accretion can occur, known as the Eddington limit. This limit arises because the radiation produced by infalling material exerts outward pressure on surrounding gas. When the radiation pressure becomes strong enough, it prevents additional gas from falling in, effectively capping the accretion rate. For a black hole accreting at the Eddington limit, its mass doubles roughly every 45 million years. Starting from a 100 solar mass stellar remnant and accreting continuously at this maximum rate, a black hole could reach about 100,000 solar masses after 430 million years. GN-z11's black hole is more than 10 times more massive than this. The math simply doesn't work unless something unusual happened. Either the black hole started from a much larger initial mass, or it accreted matter faster than the Eddington limit should allow, or both. Webb's spectrum provided evidence for super Eddington accretion. The data indicated the black hole was consuming matter at roughly 5 times the Eddington limit. This seems impossible according to standard physics, but researchers have proposed mechanisms that might allow temporary periods of enhanced accretion. One possibility involves a geometrically thick accretion disk where radiation escapes perpendicular to the disk while matter continues falling in through the disk's plane. Another involves particularly gas-rich environments where the sheer amount of available material overwhelms the radiation pressure. The early universe was indeed gas-rich, with minimal dust to absorb radiation, potentially creating conditions favourable for super Eddington growth. Even allowing for super Eddington accretion, the timing remains challenging. If GN-z11's black hole grew from a stellar mass seed at 5 times the Eddington limit, it could reach the observed mass in roughly 200 million years. This means the seed black hole must have formed by 230 million years after the Big Bang, during or shortly after the era of the first stars. This timeline is extremely tight, leaving almost no room for delays or interruptions in the accretion process. The black hole would have to begin growing almost immediately after forming, in an environment that continuously supplied massive amounts of fuel. An alternative explanation invokes direct collapse black holes. Instead of forming from stellar remnants, these black holes would form directly from the collapse of massive gas clouds. Under specific conditions, such as in pristine gas clouds where hydrogen molecules cannot form efficiently, cooling mechanisms that normally fragment clouds into smaller pieces might fail. The entire cloud, potentially weighing thousands or even hundreds of thousands of solar masses, could collapse directly into a black hole without ever forming stars. This scenario would provide the large seed masses needed to explain supermassive black holes at early times. However, direct collapse requires very special conditions that might be rare in the early universe. The gas must be metal-free, since even trace amounts of heavy elements provide efficient cooling mechanisms. The gas must also be heated by external radiation to prevent molecule formation, but not heated so much that it becomes too hot and pressure supported. The radiation environment needs to be just right, with strong ultraviolet light but minimal X-rays or cosmic rays. Only a small fraction of regions in the early universe likely met these criteria. Whether direct collapse black holes actually formed remains an open question, with no definitive observational evidence yet. The implications of GN-z11's black hole extend beyond the puzzle of its existence. The black hole was not merely sitting dormant, it was actively feeding and growing, pumping enormous amounts of energy into its surroundings. As matter spirals into a black hole, friction heats the material to millions of degrees, causing it to radiate across the electromagnetic spectrum. This radiation ionizes nearby gas, creating the emission lines Webb detected. But it also drives powerful winds that can expel gas from the galaxy entirely. These winds were evident in GN-z11 spectrum, showing velocities of several thousand kilometers per second. Such powerful outflows have profound effects on galaxy evolution. They remove the raw material for star formation, potentially quenching star formation activity. They also prevent additional gas from accreting onto the black hole itself, eventually shutting down the active galactic nucleus phase. This feedback process is thought to regulate the growth of both black holes and their host galaxies, explaining why nearly all massive galaxies contain supermassive black holes with masses that correlate tightly with the galaxy's stellar bulge mass. But in GN-z11, this feedback was just beginning. The galaxy was still forming stars vigorously despite the black hole's activity, suggesting the feedback had not yet become effective. The presence of a massive black hole in GN-z11 adds another layer of complexity to the galaxy formation problem. Not only did this galaxy assemble a billion solar masses of stars in record time, it also grew a supermassive black hole simultaneously. The coordination between these processes suggests a fundamental connection between black hole and galaxy formation that operates from the earliest epochs. Understanding this connection requires grappling with some of the most difficult problems in astrophysics. How do black holes and galaxies co-evolve? What processes regulate their growth? And what determines the final relationship between black hole mass and galaxy properties? Evidence for the first stars. Beyond the supermassive black hole, Webb's observations of GN-z11 revealed another tantalizing discovery: possible evidence for population 3 stars, the hypothetical first generation of stars in the universe. These stars have never been directly observed, but their existence is predicted by cosmological models. Formed from the pure hydrogen and helium gas left over from the Big Bang, with no heavy elements whatsoever, population 3 stars should have been fundamentally different from any stars we see today. Understanding whether they existed, and if so, what properties they had, represents one of the major goals of modern astrophysics. The theoretical picture of population 3 stars paints them as monsters. Without heavy elements to facilitate cooling, primordial gas clouds would have to collapse further and become hotter before fragmenting and forming stars. This resulted in much more massive stars than typically formed today. While contemporary star-forming regions produce mostly low-mass stars like our Sun, with massive stars being relatively rare, population 3 star formation might have been dominated by objects weighing hundreds of solar masses. These behemoths would have burned intensely hot and bright, with surface temperatures exceeding 100,000 Kelvin and luminosities millions of times greater than the Sun. Such extreme stars would have lifetimes measured in mere millions of years. They would burn through their hydrogen fuel rapidly, proceed through increasingly heavy elements via nuclear fusion, and ultimately explode as pair instability supernovae, explosions so energetic they completely destroy the star, leaving no remnant. These explosions would inject tremendous amounts of energy into the surrounding gas while enriching it with the first heavy elements. The era of pure population 3 stars would be brief, lasting only until enough supernovae had occurred to pollute the interstellar medium. After that, subsequent generations of stars would contain small but increasing amounts of metals. Webb's spectrum of GN-z11 showed something unusual in the galaxy's outer halo, a clump of gas with an elemental composition that appeared remarkably pristine. The gas was almost entirely hydrogen and helium, with little evidence for heavier elements. This pristine composition suggested the gas had not been significantly enriched by supernovae, raising the possibility that it represented leftover primordial gas from the Big Bang. Even more intriguingly, the clump showed signs of recent or ongoing star formation. If stars were indeed forming in this pristine gas, they would, by definition, be population 3 stars. The evidence was not definitive. Detecting population 3 stars directly remains extraordinarily difficult because these stars should be extremely rare in the present-day universe, having all died billions of years ago. The best hope for finding them is to observe galaxies at the highest possible redshifts, catching them during the brief window when population 3 stars still existed. Even then, distinguishing population 3 stars from the metal-poor but not metal-free stars of subsequent generations requires detailed spectroscopic analysis and careful interpretation. The pristine gas clump in GN-z11's halo was suggestive but not conclusive proof. What made this discovery particularly interesting was its location. The pristine gas sat in the galaxy's halo, separated from the main star-forming region. This spatial separation suggested a picture where the central galaxy had already been enriched by supernovae from its initial burst of star formation, while pockets of pristine gas survived in the outer regions, shielded from the metal enrichment. These pockets might now be collapsing to form a second generation of stars, this time including genuine population 3 objects alongside stars forming from slightly enriched material. This scenario would explain why GN-z11's central regions showed clear evidence of heavy elements, while its halo retained pristine gas. The implications of finding population 3 stars in GN-z11 would be profound. These stars represent the transition point between the Dark Ages and the epoch of Reionization. They produce the first light in the universe, the first heavy elements, and possibly the first stellar mass black holes. Their properties, masses, lifetimes, explosion energies directly influence how quickly the universe could form larger structures. If population 3 stars were as massive as theoretical models suggest, they would have been extraordinarily efficient at ionizing hydrogen, quickly clearing away the neutral gas that made the early universe opaque. They would also have enriched the intergalactic medium with heavy elements, changing the cooling properties of gas and affecting subsequent star formation. However, the mass distribution of population 3 stars remains highly uncertain. While models generally predict very massive stars, the details depend on assumptions about the cooling physics of metal-free gas and the fragmentation behavior of collapsing clouds. Some models suggest population 3 stars might have had a broader range of masses, including stars as small as a few solar masses alongside the supermassive ones. Lower mass population 3 stars could have longer lifetimes and might even survive to the present day, though they would be extraordinarily difficult to identify among the countless metal-poor stars in the Milky Way's halo. The search for population 3 stars has been ongoing for decades without a confirmed detection. Several candidates have been proposed over the years, including extremely metal-poor stars in the Milky Way that might be second-generation objects formed from gas enriched by just 1 or 2 population 3 stars 3 supernovae. but no star has been found with absolutely zero heavy element content. Similarly, spectroscopic studies of distant galaxies have looked for the characteristic signatures that population 3 stars should produce, such as strong helium emission and an absence of metal lines, but results have been ambiguous. GN-z11's pristine gas clump represents one of the most promising leads yet. The discovery also highlighted the capabilities of Webb's instruments. The detailed spectroscopy required to identify this pristine gas clump and characterize its composition would have been impossible with Hubble or ground-based telescopes. Webb's near-infrared sensitivity, combined with its high spectral resolution, opened a new window on the earliest phases of galaxy formation. As Webb continues to observe more distant galaxies, astronomers hope to find additional examples of pristine gas and ultimately catch population 3 stars in the act of forming. Such discoveries would validate decades of theoretical work and provide crucial constraints on models of the first stars. The pristine gas clump also raised questions about the distribution of heavy elements in the early universe. If some regions of GN-z11's halo remained unpolluted by supernovae, while the central regions were enriched, what does this imply about mixing processes in early galaxies? Modern galaxies have well-mixed interstellar media where supernova ejecta disperse relatively quickly. But perhaps in the denser, more turbulent environments of the early universe, mixing was less efficient, allowing pristine and enriched gas to coexist in close proximity. Understanding these mixing processes is important for interpreting observations of early galaxies and determining whether chemical abundances measured in spectra represent the true average composition or just reflect particular pockets of gas. Ultraviolet photons from an infant universe. One of GN-z11's most remarkable properties is its prodigious ultraviolet output. When Webb measured the galaxy spectrum, it revealed an object shining with exceptional brightness in ultraviolet wavelengths. Wavelengths that, due to the universe's expansion, appeared as near-infrared light when they reached our telescopes. The amount of ultraviolet radiation pouring out of this tiny galaxy exceeded what seemed possible from stars alone. This raised fundamental questions about what was producing so much energetic light and what effects this radiation had on the surrounding universe. Ultraviolet radiation plays a critical role in cosmic history because it's responsible for ionizing hydrogen atoms. During the epoch of Reionization, which lasted from roughly 200 million to 1 billion years after the Big Bang, the universe transitioned from being filled with neutral hydrogen gas to being largely ionized. This transition required enormous amounts of ultraviolet radiation to strip electrons from hydrogen atoms throughout the entire universe. Galaxies were the likely source of this radiation, but how many galaxies were needed and what properties they required remains an active area of research. GN-z11 represents exactly the type of object that could contribute significantly to reionization. The measurements indicated that GN-z11 produced ultraviolet photons at a rate corresponding to roughly 80 billion times the Sun's total energy output. This luminosity seems almost incomprehensible for such a small galaxy. To put it in perspective, our entire Milky Way galaxy, with its 200 to 400 billion stars, produces about 30 billion solar luminosities. GN-z11, with just 1% of the Milky Way's stellar mass, somehow generated nearly 3 times more light. The only way to achieve this is through an exceptional population of young, massive stars, combined with very little dust to absorb their radiation. Young, massive stars are ultraviolet powerhouses. A single star weighing 100 solar masses emits roughly 1 million times more light than the Sun, most of it in ultraviolet wavelengths. These stars live fast and die young, burning through their nuclear fuel in just a few million years. A galaxy experiencing a massive burst of star formation would temporarily host many such stars simultaneously, dramatically boosting its ultraviolet output. But even accounting for this, GN-z11's observed luminosity required either an extraordinarily top-heavy initial mass function, meaning far more massive stars formed than typical, or additional contributions from the central black hole. The active galactic nucleus could certainly contribute to the ultraviolet luminosity. As matter spirals into a black hole, gravitational energy converts to radiation across a broad spectrum, including substantial ultraviolet emission. However, disentangling the contributions from stars versus the black hole proved challenging. Webb's spatial resolution, while excellent, could not separate the central black hole from the surrounding star-forming regions in a galaxy so small and distant. Astronomers had to rely on spectroscopic techniques, looking for emission line ratios and continuum shapes characteristic of each source type. The evidence suggested both stars and the black hole contributed, but determining precise fractions remained difficult. The low dust content in GN-z11 was crucial to its high observed ultraviolet luminosity. Dust grains composed of carbon and silicate minerals efficiently absorb ultraviolet radiation and re-emit it at longer infrared wavelengths. In nearby star-forming galaxies, dust can absorb the majority of ultraviolet light, making these galaxies appear much dimmer in the ultraviolet than they actually are. GN-z11 spectrum showed minimal evidence for dust absorption, suggesting the galaxy contained very little dust. This made sense given its young age and low metallicity. Dust grains form from heavy elements, so galaxies with few heavy elements naturally have little dust. The lack of dust had important implications for understanding GN-z11's role in reionization. If most of the ultraviolet photons produced by stars escape the galaxy rather than being absorbed by dust, then GN-z11 could efficiently ionize the hydrogen gas in the intergalactic medium surrounding it. Observations suggested that roughly 30% of the ultraviolet photons escape the galaxy, a much higher escape fraction than seen in typical present-day star-forming galaxies. This high escape fraction meant GN-z11 punched above its weight in terms of contributing to cosmic reionization. Calculating exactly how much volume GN-z11 could ionize required knowing not only how many photons it produced, but also understanding the density and clumpiness of the surrounding neutral hydrogen. The intergalactic medium at this epoch was likely quite inhomogeneous, with dense regions and voids. Photons traveling through lower density regions could ionize hydrogen more efficiently because each photon encountered fewer hydrogen atoms before being absorbed. Dense knots of gas, conversely, would absorb photons quickly, limiting the ionized region's extent. Computer simulations of reionization suggested that individual galaxies like GN-z11 created ionized bubbles extending roughly a few million light-years in diameter, depending on local conditions. These ionized bubbles grew over time as the galaxy continued pumping out ultraviolet radiation. Eventually, bubbles around different galaxies would merge, creating larger ionized regions. The process was self-accelerating in some ways because ionized regions have different thermal properties than neutral gas, potentially affecting how gas collapsed to form new galaxies. The feedback between galaxy formation and reionization represents a complex interplay that simulation teams were still working to understand fully. GN-z11 provided a real-world example of a reionization source in action, offering empirical constraints on these theoretical models. The intensity of ultraviolet radiation in GN-z11's immediate vicinity would have been extreme. Stars and gas clouds within the galaxy experience radiation fields orders of magnitude stronger than anything in our present-day Milky Way. This intense radiation had multiple effects. It ionized gas in the galaxy's interstellar medium, creating large regions of hot plasma. It heated dust grains to high temperatures, causing them to evaporate in some cases. It photo-evaporated the outer layers of molecular clouds, potentially disrupting star formation in some regions while triggering it in others through compression effects. The environment inside GN-z11 would have been incredibly harsh by modern standards. One particularly interesting aspect of GN-z11's ultraviolet output concerned the Lyman alpha emission line, a specific wavelength of light produced when electrons in hydrogen atoms drop from their second excited state to the ground state. This line is one of the brightest features in the spectra of star-forming galaxies, and it serves as a powerful diagnostic tool. However, Lyman alpha photons scatter easily off neutral hydrogen atoms, meaning they struggle to escape from galaxies surrounded by neutral gas. GN-z11 spectrum showed strong Lyman alpha emission, suggesting the gas immediately around the galaxy was largely ionized, creating a pathway for these photons to escape. The presence of strong Lyman alpha emission also helped confirm GN-z11's distance. At very high redshifts, approaching the end of the epoch of reionization, the intergalactic medium contains increasing amounts of neutral hydrogen. This neutral gas absorbs Lyman alpha photons traveling from distant galaxies toward Earth, suppressing or eliminating the Lyman alpha line in observed spectra. The fact that GN-z11 showed strong Lyman alpha indicated that the line of sight between the galaxy and Earth passed through mostly ionized gas. Combined with other spectral features, this observation painted a picture of a galaxy that had successfully ionized its local environment, creating a clear window through which its light could escape. Theoretical models predicted that galaxies like GN-z11, with their high ultraviolet output and efficient photon escape, represented the primary drivers of cosmic reionization. But uncertainties remained about how common such galaxies were. If GN-z11 was typical of early galaxies, then relatively few objects would be needed to reionize the universe. If it was exceptional, then many more galaxies would be required, most of them too faint for even Webb to detect easily. Early results from Webb's deep surveys suggested that bright galaxies like GN-z11 were somewhat more common than expected, potentially easing the requirements for completing reionization. However, the full census of the early galaxy population remained incomplete, and whether observed galaxies could produce enough ionizing photons to explain the observed reionization timeline was still debated. The star formation mystery. GN-z11 star formation rate presents one of the most perplexing aspects of the entire puzzle. Converting 20 solar masses of gas into stars every year doesn't sound extraordinary compared to the most vigorous starburst galaxies in the present-day universe, some of which form stars at rates exceeding 1,000 solar masses per year. But context matters enormously. Those local starburst galaxies are massive systems containing hundreds of billions of solar masses of existing stars, built up over billions of years of cosmic history. GN-z11 achieved 1/50th the star formation rate with 100th the stellar mass in 1/30th the time. The efficiency is staggering. Star formation efficiency is typically defined as the fraction of available gas that actually forms stars within a given time period. In modern galaxies, this efficiency is notoriously low. Only a few % of molecular gas converts to stars per the typical time it takes for gas to collapse, with the rest being dispersed by various feedback mechanisms or simply failing to collapse. Yet GN-z11's properties implied a much higher efficiency, possibly 10 to 20% or even higher. What allowed such efficient star formation, and why don't we see similar efficiencies in nearby galaxies? Part of the answer may lie in the gas properties themselves. The gas in GN-z11 was likely denser and more compact than gas in present-day star-forming regions. Higher density means stronger self-gravity, helping clouds collapse despite turbulent motions that would otherwise tear them apart. The gas was also relatively metal-poor, though not completely pristine. Counterintuitively, metal-poor gas might actually form stars more efficiently under certain conditions, because it contains less dust, reducing radiation pressure from newly formed stars. Without dust to absorb and scatter stellar light, photon pressure has less effect on preventing cloud collapse. The galaxy's small size also mattered. In a compact system, gas doesn't have to travel far to reach the star-forming regions. This means the timescale for gas to be replenished is short, allowing sustained high star formation rates. In large galaxies, gas might take hundreds of millions of years to flow from the outer regions to the star-forming disk. GN-z11's compactness meant fresh gas was always nearby, ready to collapse and form new stars. This short replenishment timescale could help maintain the observed star formation rate even as feedback processes tried to disrupt ongoing star formation. Feedback processes themselves might have operated differently in the early universe. Modern star-forming regions experience feedback from several sources: stellar winds from massive stars, ionizing radiation that heats and pressurizes gas, and supernova explosions that inject energy and momentum. Each of these can disrupt molecular clouds and prevent further star formation. But in the dense, metal-poor environment of GN-z11, these feedback mechanisms might have been less effective. Low metallicity means fewer heavy elements to absorb radiation and convert it to thermal energy. Dense gas requires more energy to disperse. The combination could allow star formation to continue longer before feedback quenches it. There's also the question of gravitational instability. In a rapidly growing galaxy experiencing frequent mergers and accretion events, the gas disk can become gravitationally unstable, fragmenting into dense clumps that collapse to form stars. This process, known as disk fragmentation, can drive very high star formation rates because it bypasses the usual step of forming molecular clouds first. The gas goes directly from a warm, diffuse state to collapsing clumps. Evidence from simulations suggested that gravitational instabilities were common in high redshift galaxies, potentially explaining their high star formation rates. GN-z11 might have been in such an unstable state. The stellar initial mass function also plays a crucial role. This function describes the relative numbers of stars formed at different masses, and it has profound implications for a galaxy's observable properties. In nearby galaxies, the IMF is bottom-heavy, meaning most stars are low-mass objects like red dwarfs. For every massive star that forms, hundreds of low-mass stars are born. But theoretical arguments suggest the IMF might have been different in the early universe, possibly shifted toward more massive stars due to different gas temperatures and densities. A top-heavy IMF would boost ultraviolet luminosity because massive stars are so much brighter than low-mass stars, potentially explaining GN-z11's exceptional brightness without requiring such extreme star formation rates. However, a top-heavy IMF creates its own problems. Massive stars die quickly in supernova explosions, injecting tremendous amounts of energy into their surroundings. If GN-z11 had been forming mostly massive stars for hundreds of millions of years, the cumulative supernova energy would be enormous, possibly enough to blow away all remaining gas and shut down star formation entirely. The fact that GN-z11 was still forming stars vigorously suggested either that the IMF wasn't extremely top-heavy, or that gas was being replenished fast enough to replace what supernovae expelled, or that the galaxy was somehow able to retain gas despite the energetic feedback. Webb's observations provided some constraints on these questions through detailed analysis of the stellar population. By measuring the strengths of various absorption and emission lines in the spectrum, astronomers could estimate the ages of stars in the galaxy and construct a rough star formation history. The data indicated that star formation in GN-z11 had been ongoing for at least 100 million years, possibly longer. This ruled out scenarios where the galaxy was observed during a brief, exceptional starburst that would fade quickly. GN-z11's high star formation rate appeared to be sustained, not transient. The sustained nature of the star formation made the puzzle worse in some ways. A brief starburst could be explained by a recent major merger or some other triggering event that temporarily drove gas inflows and star formation to extreme levels. But sustained star formation at such high rates required a continuous supply of gas and mechanisms to prevent feedback from quenching star formation. Where was all this gas coming from? The most likely source was accretion from the intergalactic medium along cosmic filaments, but even this had limits. The accretion rate was set by cosmological parameters and the mass of the dark matter halo, and it wasn't clear that cold accretion could supply gas fast enough to explain GN-z11's demands. Some researchers propose that GN-z11 sat at the intersection of multiple cosmic filaments, allowing it to accrete gas from several directions simultaneously. Such locations were rare, but did exist in simulations of large-scale structure formation. A galaxy fortunate enough to form at such a node would have access to substantially more gas than typical galaxies, potentially explaining its exceptional properties. However, this explanation was somewhat unsatisfying because it relied on GN-z11 being special rather than revealing something general about early galaxy formation. Another consideration was whether the star formation rate measurements themselves might be uncertain. Astronomers infer star formation rates from observable quantities like ultraviolet luminosity, hydrogen emission line strength, or infrared luminosity from dust-reheated starlight. Each method makes assumptions about the stellar population, dust properties, and other factors. In GN-z11's case, the low metallicity and unusual conditions might have made these assumptions less reliable. Perhaps the actual star formation rate was lower than estimated, reducing the tension with theoretical models. However, multiple independent methods all pointed to similarly high rates, suggesting the measurement was robust. The star formation mystery in GN-z11 ultimately connected to broader questions about galaxy formation in the early universe. Were all early galaxies forming stars this efficiently, or was GN-z11 unusual? If such efficiency was common, it would help explain how galaxies assembled their stellar masses so quickly, but it would also require revising our understanding of star formation physics. If GN-z11 was unusual, then understanding what made it special became the key question. The answer likely involved some combination of environmental effects, halo mass, merger history, and perhaps some luck. Determining which factors mattered most required observing many more early galaxies and looking for patterns. The chemical enrichment problem. When Webb analysed GN-z11's spectrum in detail, the chemical composition revealed another layer to the mystery. The galaxy showed clear signatures of heavy elements, including carbon, nitrogen, oxygen, and potentially even iron. These elements didn't exist in the early universe. They had to be created through nuclear fusion inside stars and then distributed into the interstellar medium through stellar winds and supernova explosions. The presence of these elements in GN-z11, just 430 million years after the Big Bang, created yet another timing problem that challenged standard models of chemical evolution. The process of chemical enrichment follows a predictable sequence. The first stars form from pure hydrogen and helium. When massive stars exhaust their hydrogen fuel, they begin fusing helium into carbon and oxygen. Even more massive stars continue up the periodic table, creating neon, magnesium, silicon, sulfur, and eventually iron. When these stars explode as supernova, they eject these newly formed elements into space. the enriched gas mixes with pristine material, slightly increasing the heavy element content. Subsequent generations of stars form from this enriched gas, creating more heavy elements when they die. With each generation, the metallicity, the fraction of elements heavier than helium, gradually increases. This process takes time. A massive star weighing 50 solar masses lives for about 3 million years before exploding. Lighter massive stars, say 20 solar masses, survive for 10 million years. The enriched gas from these explosions must then mix with surrounding material, cool and collapse to form new stars. One complete cycle, from star formation through stellar death to the next generation of star formation, requires roughly 10 to 30 million years under typical conditions. By the time we observe GN-z11 at 430 million years after the Big Bang, there had been time for perhaps 10 to 20 such cycles, depending on how quickly each proceeded. The measured metal abundances in GN-z11 were not extremely high by modern standards. The Galaxy's metallicity was roughly 2 to 5% of solar values, but they were surprisingly high for such an early galaxy. Achieving even this modest enrichment level required multiple generations of stars. Each generation would contribute some fraction of the heavy elements we observed, building up the total metallicity step by step. The tight timeline meant these cycles must have proceeded rapidly, with minimal delays between generations. Any interruption, say if supernova feedback temporarily shut down star formation for tens of millions of years, would have prevented the observed enrichment from accumulating in time. More puzzling still was the relative abundance pattern. Different types of supernovae produce different mixes of elements. Core collapse supernovae, which occur when massive stars exhaust their fuel, produce lots of oxygen and lighter elements, but relatively less iron. Type ER supernovae, which result from exploding white dwarf stars in binary systems, produce large amounts of iron and nickel. The two types have different timescales. Core collapse supernovae happen within millions of years of star formation, while type II supernova require at least 100 million years, because white dwarfs must first form and then gradually accrete matter from a companion star until they reach critical mass. GN-z11 spectrum showed evidence for both oxygen and iron, suggesting contributions from both supernova types. The presence of iron was particularly surprising because it implied type IR supernovae had already begun occurring. This meant some stars had gone through their entire life cycles, become white dwarfs, found themselves in binary systems, accreted sufficient mass, and finally exploded, all within that 430 million year window. The minimum timescale for this sequence was about 100 million years, leaving only 330 million years for the earlier phases of galaxy assembly and the initial generations of star formation. Every step had to proceed at near maximum speed. The nitrogen abundance provided another clue. Nitrogen has complex nucleosynthesis origins. Primary nitrogen is produced directly from hydrogen and helium through the CNO cycle in massive stars. Secondary nitrogen requires seed carbon and oxygen from previous stellar generations, making it a tracer of multi-generation enrichment. GN-z11 spectrum showed strong nitrogen emission, and analysis suggested both primary and secondary nitrogen were present. This reinforced the picture of rapid chemical evolution, with multiple stellar generations contributing to the observed abundances. Theoretical models of chemical evolution struggled to reproduce GN-z11's composition in the available time. Standard models, calibrated on nearby galaxies, predicted that galaxies at GN-z11's redshift should have substantially lower metallicities. Even optimistic models that assumed very efficient star formation and rapid cycling struggled to match the observations without fine-tuning parameters. Some researchers suggested that the stellar initial mass function in the early universe might have been biased toward masses that maximize heavy element production, around 20 to 30 solar masses. Such stars live just long enough to enrich the interstellar medium before exploding, optimizing the chemical evolution rate. Another possibility involved pair instability supernovae, an exotic type of explosion predicted to occur in extremely massive stars, weighing 140 to 260 solar masses. These stars become so hot in their cores that photons begin converting into electron-positron pairs, suddenly reducing the pressure support and causing catastrophic collapse. The resulting explosion is extraordinarily energetic, completely destroying the star and ejecting all its material, including large amounts of heavy elements. If the first generations of stars included such supermassive objects, they could have enriched the interstellar medium very rapidly and efficiently. However, pair instability supernovae have never been conclusively observed, and their existence remains theoretical. The distribution of metals within GN-z11 also mattered. If metals were concentrated in the galaxy's central regions, where star formation was most active, while the outskirts remained relatively pristine, this would suggest limited mixing efficiency. The spectrum represented light integrated over the entire galaxy, so it provided an average metallicity. Detailed spatially resolved spectroscopy could potentially reveal metallicity gradients, offering insights into how efficiently supernova ejecta mixed with surrounding gas. Unfortunately, GN-z11 was too small and distant for even Webb to spatially resolve its internal structure in spectroscopic observations. The role of the central black hole in chemical enrichment remained unclear. While black holes themselves don't produce heavy elements, the powerful winds driven by active galactic nuclei can distribute metals throughout a galaxy and even expel them into the intergalactic medium. If GN-z11's black hole had been active for a substantial fraction of the galaxy's lifetime, its winds could have helped spread metals from the star-forming regions to the outer halo. Conversely, if the black hole only recently became active, it would have had minimal impact on the observed metallicity distribution. Determining the black hole's activity, history required comparing the observed metal abundances with predictions from models that included AGN feedback. One intriguing aspect of the enrichment pattern was what it revealed about the galaxy's formation history. If GN-z11 had assembled through mergers of smaller proto-galaxies, each bringing its own enriched gas, the combined metallicity could be higher than if the galaxy had grown through continuous accretion of pristine intergalactic gas. Mergers also trigger starbursts by funneling gas toward the center, accelerating both star formation and chemical evolution. The observed properties were consistent with GN-z11 being the product of multiple merger events, though proving this conclusively would require detecting companion galaxies or tidal features that served as smoking guns of past interactions. The chemical composition also had implications for dust formation. Dust grains form from heavy elements, condensing out of gas ejected by evolved stars and supernova. The relatively low metallicity in GN-z11 meant dust production should have been limited, consistent with the minimal dust absorption seen in the spectrum. However, some models suggested that even small amounts of dust could have significant effects on cooling and star formation. Dust provides additional cooling channels for gas, helping it collapse more efficiently. As GN-z11's metallicity gradually increased, dust formation would have accelerated, potentially changing the galaxy's star formation properties over time. Looking at the broader context, GN-z11's chemical enrichment pattern raised questions about whether it was representative or exceptional. If most galaxies at this epoch showed similar enrichment levels, it would suggest that chemical evolution proceeded quickly throughout the early universe, requiring revisions to standard models. If GN-z11 was metal-rich compared to its peers, it would suggest special circumstances, perhaps related to its high star formation rate or central black hole. Early results from Webb surveys of high redshift galaxies suggested some diversity in metallicities, with GN-z11 appearing toward the higher end of the distribution. This hinted that it might indeed be somewhat special, though more data was needed to establish the full range of properties among early galaxies. Comparing theories against reality. The lambda cold dark matter model has proven remarkably successful at explaining cosmic structure on the larger scales. It accurately predicts the pattern of temperature fluctuations in the cosmic microwave background, the distribution of galaxies in large surveys, and the properties of galaxy clusters. The model's success stems from its relative simplicity. It assumes that dark matter is cold, meaning it moves slowly compared to the speed of light, and that dark energy drives accelerated cosmic expansion. With just 6 adjustable parameters, lambda CDM can reproduce a vast array of observations. But GN-z11 represents a challenge at smaller scales, where the model's predictions become less certain. At the heart of lambda CDM is a statistical framework describing how initial density fluctuations grow over time. The universe after the Big Bang was not perfectly uniform. Quantum fluctuations during inflation created tiny variations in density, with some regions slightly denser and others slightly less dense. Gravity amplified these variations over time. Dense regions attracted more matter, becoming denser still, while underdense regions lost matter and became emptier. This process created the cosmic web of structure we see today, with galaxies sitting at the intersections of filaments while vast voids separate them. The model makes specific predictions about when structures of different masses should form. Small dark matter halos collapse first, at redshifts of 30 or higher, just tens of millions of years after the Big Bang. Progressively larger halos formed later as the initially separate small halos merged. By the time we observe GN-z11 at redshift 11, halos weighing 1 billion solar masses or more should have been rare, but not impossible. The dark matter in these halos provides the gravitational potential wells that attract ordinary matter, setting the stage for galaxy formation. But translating from dark matter halos to luminous galaxies requires understanding complex astrophysics. This is where theoretical models become uncertain. Dark matter is relatively simple. It only interacts gravitationally, making its behavior straightforward to simulate. Ordinary matter, however, undergoes complicated processes, including cooling, heating, star formation, feedback from supernova and active galactic nuclei, magnetic fields, turbulence, and chemical enrichment. No simulation can capture all these processes with perfect accuracy. Researchers must make approximations, implementing subgrid models for phenomena that occur on scales smaller than the simulation's resolution. Different modeling choices lead to different predictions, introducing uncertainties that grow larger when looking at individual galaxies rather than statistical averages. Semi-analytic models represent one approach to galaxy formation. These models start with dark matter halos from lambda CDM simulations, then apply simplified recipes for gas cooling, star formation, and feedback. The recipes contain adjustable parameters calibrated to match observed properties of nearby galaxies. Such models can run quickly, allowing exploration of parameter space and statistical predictions for large galaxy populations. When applied to the early universe, semi-analytic models generally predicted that bright galaxies like GN-z11 should be extremely rare at redshift 11. The predicted number density of galaxies with GN-z11's luminosity was roughly 1 per billion cubic megaparsecs, making it a rare outlier that shouldn't be easily detectable. Hydrodynamic simulations take a different approach, directly solving the equations of fluid dynamics for gas, while simultaneously tracking dark matter. These simulations are computationally expensive, but can provide more realistic treatments of gas physics. State-of-the-art simulations include sophisticated models for star formation, supernova and AGN feedback, chemical evolution, and even individual stellar population evolution. When run with initial conditions matching our universe's observed properties, these simulations produce virtual universes that can be directly compared with observations. Results from major simulation projects suggested that while galaxies like GN-z11 were rare, they should exist in the volumes surveyed by deep fields like GOODS North. However, getting the detailed properties right proved challenging. Simulations that successfully reproduce the average properties of galaxies at lower redshifts often struggled at the highest redshifts. The star formation rates predicted for high redshift galaxies were frequently too low, requiring adjustments to feedback models or star formation efficiencies. The size evolution also caused problems. Observed high redshift galaxies appeared systematically more compact than simulated ones, suggesting either that simulations overestimated the amount of angular momentum in the gas, or that feedback processes weren't efficiently removing outer gas layers. GN-z11's extreme compactness and high star formation rate made these discrepancies particularly acute. Some researchers argued that the issues arose from incomplete physics in the simulations. Magnetic fields, for instance, were often neglected or treated in simplified ways, yet they could significantly affect gas dynamics and star formation. Cosmic rays, high-energy particles accelerated by supernovae and active galactic nuclei, were similarly omitted from most simulations despite potentially providing important additional pressure support against gravitational collapse. Turbulence operating on scales below the simulation resolution was typically handled with approximate subgrid models that might miss important effects. Each omitted or approximated process introduced uncertainties that accumulated when making predictions about individual galaxies. Alternative cosmological models offered different perspectives on the problem. Some researchers proposed modifications to lambda-CDM that would enhance structure formation at early times. These included models with slightly different dark matter properties, such as warm dark matter that moves faster than cold dark matter, or models invoking interactions between dark matter and dark energy. Such modifications could potentially shift the timeline of galaxy formation, allowing bright galaxies to appear earlier. However, these alternative models face stringent constraints from other observations, particularly the cosmic microwave background and the large-scale distribution of galaxies. Most struggled to explain GN-z11 while simultaneously matching these other observations. The possibility of primordial black holes garnered some attention. If a significant fraction of dark matter consisted not of exotic particles, but of black holes formed in the very early universe, this could affect structure formation. Primordial black holes could seed galaxy formation, providing the massive black holes needed to explain GN-z11's central engine without requiring rapid growth from stellar remnants. However, constraints from gravitational lensing, the cosmic microwave background, and gravitational wave observations place severe limits on the abundance of primordial black holes across most mass ranges. They could at most comprise a small fraction of total dark matter, likely insufficient to explain GN-z11's properties. Another line of thinking focused on initial conditions. Standard inflationary models predict a nearly scale invariant spectrum of density fluctuations, meaning fluctuations at different scales have similar amplitudes. But small deviations from scale invariance are allowed and could significantly affect rare objects like GN-z11. If the primordial power spectrum had slightly more power on small scales than the standard prediction, it would boost the formation of the first structures, potentially explaining the early appearance of bright galaxies. Testing this idea required careful measurements of the power spectrum from multiple independent probes, including the cosmic microwave background, gravitational lensing, and the galaxy distribution at various redshifts. The comparison between theory and observation ultimately revealed tensions rather than outright contradictions. GN-z11 was rare enough that its existence could be accommodated within lambda CDM, though it sat in the extreme tail of the predicted distribution. The model predicted perhaps one such galaxy in the volume observed by deep surveys, and one is what was found. The problem was that GN-z11's detailed properties, its stellar mass, star formation rate, black hole mass, and chemical enrichment, all pushed or exceeded what models predicted. While each property individually might be explained by assuming favourable conditions or adjusting parameters, explaining all of them simultaneously in a single object proved difficult. JWST's census of early galaxies. When the James Webb Space Telescope began its scientific operations in 2022, one of its primary missions was conducting deep surveys of the early universe. These surveys aimed to find not just individual exceptional objects like GN-z11, but entire populations of galaxies across cosmic time. By observing hundreds or thousands of galaxies at various redshifts, astronomers could determine whether GN-z11 represented a rare outlier or the bright end of a common population. The answer would have profound implications for understanding galaxy formation and the validity of the lambda CDM model. The Cosmic Evolution Early Release Science Survey, or CERS, was among the first major programs to search for high redshift galaxies. Operating in the extended Groth Strip, a region extensively studied by previous telescopes, CERS imaged thousands of galaxies with Webb's near-infrared camera. The survey reached unprecedented depths, detecting galaxies fainter than anything Hubble could see at these wavelengths. Within the first few months of observation, CERS identified dozens of candidate galaxies at redshifts beyond 9, pushing into the epoch where GN-z11 resided. These candidates awaited spectroscopic confirmation, but their sheer numbers suggested that bright early galaxies might be more common than pre-Webb theoretical predictions indicated. The JD survey, JWST Advanced Deep Extragalactic Survey, took an even deeper approach, targeting the Hubble ultra-deep field and the Goods fields, with extremely long exposure times. JAIS combined imaging in multiple near-infrared filters with extensive spectroscopic follow-up, allowing precise redshift measurements for hundreds of galaxies. By early 2023, JAIS had discovered several galaxies with spectroscopically confirmed redshifts beyond 10, and numerous candidates pushing toward redshift 15 or even higher. These objects appeared surprisingly bright and numerous compared to what extrapolations from lower redshift data had suggested. Among the JAIS discoveries was a galaxy designated JAIS GN-z11, which held the spectroscopic distance record before later discoveries pushed further. With a redshift of 13.2, this galaxy existed just 330 million years after the Big Bang, even earlier than GN-z11. It showed active star formation and, like GN-z11, appeared more luminous than models had predicted for such early times. The similarities between JAIS GS-z13-0 and GN-z11 suggested that the latter might not be as exceptional as first thought. Perhaps vigorous star formation and rapid mass assembly were relatively common among galaxies in this epoch, at least among the brightest examples that Webb could detect. Statistical analyses of the early galaxy population revealed a striking pattern. The number of bright galaxies at high redshifts exceeded predictions from pre-Webb models by factors of 3 to 10, depending on the exact redshift and luminosity range examined. This excess was most pronounced for the very brightest galaxies, objects like GN-z11 that should have been extremely rare. The observation suggested either that the star formation efficiency in early galaxies was higher than models assumed, or that the galaxy stellar mass function evolved differently than predicted, or both. Either way, something about early galaxy formation was not captured by existing theoretical frameworks. The situation grew more complex as Webb discovered galaxies at even higher redshifts. By late 2023 and into 2024, candidate galaxies at redshifts beyond 15 had been identified, though spectroscopic confirmation for the highest redshift objects remained challenging. If confirmed, these galaxies would have existed less than 300 million years after the Big Bang, during or immediately after the formation of the first stars. Their luminosities implied stellar masses that should have been impossible to assemble so quickly, according to standard hierarchical formation models. Each new discovery tightened the constraints on theory and deepened the challenge to lambda CDM. Not all researchers agreed on the interpretation. Some argued that photometric redshift estimates for the most extreme candidates were uncertain, and that spectroscopic follow-up would reveal lower redshifts for many objects. Photometric techniques can be fooled by unusual spectral features or dust extinction patterns, potentially placing galaxies at incorrect distances. A few early photometric candidates did turn out to be at lower redshifts than initially estimated when spectra were obtained. However, enough spectroscopic confirmations accumulated to establish that bright galaxies at redshifts beyond 10 were indeed more common than expected, even accounting for uncertainties. The nature of these early galaxies also came under scrutiny. Some showed irregular morphologies suggesting ongoing mergers or violent processes. Others appeared surprisingly smooth and compact, more like proto-elliptical galaxies than the clumpy star-forming systems typical of lower redshift galaxies. The diversity of morphologies indicated that different formation pathways were operating, with some galaxies assembling through mergers while others grew through steady accretion. Understanding which pathways dominated and how they related to galaxy properties required analysing large samples, work that was ongoing as Webb data continued accumulating. The stellar populations in these early galaxies provided crucial information. By analysing the shapes of their spectral energy distributions, the amount of light emitted at different wavelengths, astronomers could estimate the ages and masses of their stellar populations. Some early galaxies showed evidence for old stars, meaning stars that had formed even earlier and had already evolved off the main sequence. This pushed back the era of significant star formation to redshifts beyond 20, less than 200 million years after the Big Bang. Such early star formation was difficult to reconcile with hierarchical formation models, which predicted a gradual buildup of stellar mass rather than intense early bursts. The black hole population at high redshifts added another dimension to the census. Webb's spectroscopic capabilities allowed detection of active galactic nuclei through their characteristic emission line patterns. Several high redshift galaxies showed evidence for massive black holes similar to GN-z11s, weighing millions of solar masses despite existing less than 500 million years after the Big Bang. The black hole mass function at these early times appeared to be surprisingly similar to that at lower redshifts, suggesting that massive black holes formed and grew rapidly in the early universe. This reinforced the timing problem discussed earlier. How did these black holes assemble so quickly? The implications for reionization became increasingly important as the high redshift galaxy census grew. If bright galaxies were more numerous than expected, they could contribute significantly more ionizing photons than previously assumed. This would help complete reionization earlier or with fewer low-mass galaxies than required in previous models. Conversely, if these bright galaxies hosted massive black holes that drove strong winds, they might expel gas and reduce their effective contribution to reionization. Disentangling these effects required detailed modelling of both stellar populations and AGN activity, work that depended on having large samples of galaxies with well-characterized properties. One emerging pattern from Webb surveys was that galaxy properties evolved rapidly between redshift 15 and redshift 6. Star formation rates, stellar masses, sizes and morphologies all showed strong evolution over this period. The rate of change was faster than seen at lower redshifts, suggesting that the early universe was a particularly dynamic era for galaxy formation. GN-z11, observed during this period, captured galaxies during a critical transition phase when they were building up mass rapidly while simultaneously enriching themselves with heavy elements and growing their central black holes. Understanding this transition was key to connecting the first stars with the mature galaxies seen at later times. The kinematics of ancient stars. Understanding how gas and stars move within GN-z11 provides crucial insights into the galaxy's structure, mass and formation history. Kinematics, the study of motion without reference to forces, reveals whether a galaxy is rotating like a disk, dispersed like an elliptical galaxy, or displaying the complex motions characteristic of ongoing mergers. For GN-z11, obtaining kinematic measurements pushed Webb's capabilities to their limits, but the results offered tantalizing clues about how this ancient galaxy was assembled and how it might evolve. Spectroscopy provides kinematic information through the Doppler effect. When gas or stars move toward us, the wavelengths of light they emit are compressed, shifting toward blue. When moving away, wavelengths stretch toward red. By measuring how spectral lines shift across a galaxy's extent, astronomers can map the velocity field and determine whether the galaxy shows ordered rotation or random motions. For nearby galaxies, such measurements are routine. For an object as distant and compact as GN-z11, they represent an extraordinary technical challenge. Webb's integral field spectrograph mode allowed spatially resolved spectroscopy of GN-z11, though with limited spatial resolution. The data suggested that the galaxy showed some degree of rotation, with one side of the galaxy systematically redshifted relative to the other. This indicated that GN-z11 possessed angular momentum and was spinning, at least to some extent. The rotation velocity was estimated at roughly 120 kilometers per second, comparable to rotation speeds in dwarf galaxies in the present-day universe. This might seem slow compared to the Milky Way's rotation speed of 220 kilometers per second, but for a galaxy as compact as GN-z11, it represented significant angular momentum. However, the rotation was not clean or well-ordered. The velocity dispersion, the spread in velocities at any given location, was quite high, around 90 kilometers per second. This large dispersion indicated substantial random motions beyond the ordered rotation. In dynamical terms, the galaxy had a relatively low ratio of ordered to random motion, characteristic of a thick disk or a dispersion-dominated system rather than a thin, rotation-supported disk like the Milky Way. This suggested GN-z11 was not yet dynamically relaxed, possibly because it had recently experienced mergers or was undergoing violent disk instability. The combination of rotation and high dispersion has specific implications for the galaxy's mass. In a rotating system, the rotation speed relates to the enclosed mass through gravitational dynamics. A faster rotation implies more mass pulling the gas and stars into orbital motion. Similarly, velocity dispersion relates to mass through the virial theorem, which connects kinetic and potential energy in gravitationally bound systems. Using both rotation and dispersion, astronomers could estimate GN-z11's dynamical mass, the total mass of all matter, including dark matter within the observed region. The dynamical mass estimate came out to roughly 2 to 3 billion solar masses. This exceeded the stellar mass of 1 billion solar masses, with the difference presumably representing dark matter and gas. The ratio of dynamical to stellar mass was comparable to what's seen in low-mass galaxies today, suggesting GN-z11 resided in a dark matter halo weighing several billion solar masses. This halo mass was consistent with lambda CDM predictions for galaxies at this redshift and luminosity, though it sat at the high end of the predicted range. The agreement between dynamical and stellar mass estimates provided reassuring confirmation that the various measurement methods were reliable. The galaxy's high-velocity dispersion raised questions about its future evolution. Dispersion-dominated systems tend to evolve into elliptical-like galaxies through a process called violent relaxation, where gravitational interactions during mergers scatter stars into random orbits. If GN-z11 continued experiencing mergers, it might eventually form the core of a massive elliptical galaxy. Alternatively, if it avoided major mergers and continued accreting gas smoothly, the disk might gradually settle and become more rotation-dominated as new stars formed in circular orbits. The ultimate outcome depended on factors like the merger rate and gas supply that were difficult to predict from a single snapshot observation. The detection of outflows provided additional kinematic information. Webb's spectrum showed blue-shifted absorption lines indicating gas moving toward us at velocities up to several thousand kilometers per second. These high velocities far exceeded the galaxy's escape velocity, meaning the gas was unbound and being expelled from the system entirely. The outflow rate, estimated from the absorption line strengths and velocities, was comparable to or slightly exceeding the star formation rate. This meant GN-z11 was expelling as much gas as it was converting into stars, a situation sometimes called a gas fountain, where outflows might eventually return and recycle. The driving mechanism for these outflows was likely a combination of supernova feedback and AGN winds. Supernovae inject energy and momentum through blast waves that sweep up surrounding gas. Multiple supernovae in a concentrated star-forming region can create superbubbles that eventually break out of the galactic disk, launching fountains of hot gas. The active galactic nucleus contributed through radiation pressure and relativistic jets or winds powered by accretion onto the central black hole. Disentangling the relative contributions of stellar and AGN feedback required detailed modelling that matched the observed outflow properties. The implications of these outflows for galaxy evolution were significant. Mass loss through winds removes gas that could otherwise form stars, potentially regulating or even quenching star formation. It also removes heavy elements that supernovae had previously injected, expelling them into the circumgalactic medium or intergalactic space. This metal ejection enriched the intergalactic medium, affecting the properties of gas that would later accrete onto other galaxies. In this sense, galaxies like GN-z11 acted as chemical factories, processing primordial gas through stars and then distributing the products across cosmic scales. The geometry of the outflows mattered for understanding their effects. If winds were predominantly bipolar, flowing along the galaxy's rotation axis, they might clear paths for ionizing radiation to escape while leaving equatorial gas intact for continued star formation. If winds were more isotropic, expanding in all directions, they would more effectively remove gas from the entire galaxy. Webb's limited spatial resolution made determining the outflow geometry challenging, but some evidence suggested preferential outflow directions, possibly aligned with the rotation axis or driven by the AGN's orientation. Comparing GN-z11's kinematics with those of galaxies at lower redshifts revealed interesting patterns. The ratio of rotation velocity to velocity dispersion appeared to increase with cosmic time, suggesting galaxies gradually became more settled and disk-like. This evolution made sense in the context of hierarchical formation. Early galaxies experienced frequent mergers and violent processes that stirred up random motions, while later galaxies had more time to settle into equilibrium configurations. GN-z11 caught early in this evolutionary sequence, displayed the dynamical signatures of youth. Substantial angular momentum, but not yet organised into a thin, well-ordered disk. The magnification question. One of the first questions astronomers asked when GN-z11's extraordinary properties became apparent was whether gravitational lensing might be inflating its observed brightness. Gravitational lensing occurs when massive foreground objects bend the path of light from background sources, potentially magnifying their apparent luminosity by factors of 2, 10, or even hundreds. If GN-z11 were being magnified by a factor of 5 or 10, its intrinsic properties would be correspondingly less extreme, potentially easing some of the theoretical tensions. Determining whether lensing played a role required careful analysis of the foreground mass distribution and searches for telltale lensing signatures. The first indication that GN-z11 was not strongly lensed came from its morphology. Strongly lensed galaxies typically appear as multiple images or show characteristic arc-like distortions when viewed through a gravitational lens. Webb's high-resolution images of GN-z11 showed a compact, roughly circular morphology with no obvious signs of distortion or multiplicity. The galaxy appeared as a single, well-defined object, rather than the elongated arcs or multiple images that characterize strong lensing events. This morphological evidence suggested that if lensing was occurring, it was weak rather than strong. Weak gravitational lensing can still magnify objects, but by more modest factors, typically between 1 and 3. Even weak magnification required the presence of significant foreground mass along the line of sight. Astronomers searched the field around GN-z11 for foreground galaxies or galaxy clusters that could act as lenses. The GOODS-north field had been studied extensively, and its foreground mass distribution was well characterized. No massive galaxy clusters lay directly in front of GN-z11. The foreground contained individual galaxies at various redshifts, but none positioned perfectly to produce significant lensing magnification. Theoretical calculations confirmed these observational assessments. By modelling the mass distribution along the line of sight using observations of foreground galaxies and large-scale structure simulations, researchers estimated the expected magnification factor. The results indicated a magnification of only about 1.1 to 1.2, essentially negligible compared to GN-z11's extraordinary properties. Even accounting for uncertainties in the mass models, magnification factors above 2 could be ruled out with high confidence. This meant that GN-z11's observed luminosity and inferred properties were essentially intrinsic, not artificially boosted by lensing. The absence of significant lensing magnification had important implications. It meant that the galaxy's challenges to theoretical models were real and could not be dismissed as observational artifacts. The billion solar masses of stars, the intense star formation rate, the supermassive black hole, and the high chemical enrichment were all genuine properties that theories needed to explain. If anything, the lack of lensing made the puzzle worse because it eliminated one potential explanation for the galaxy's exceptional brightness. However, weak lensing does affect statistical studies of high redshift galaxy populations, even if individual galaxies like GN-z11 show minimal magnification. When surveying large volumes of space for distant galaxies, some fraction will be magnified by factors of 2 or 3 due to chance alignments with foreground mass concentrations. This magnification bias means that flux-limited surveys preferentially detect magnified objects, potentially skewing measurements of the galaxy luminosity function. Correcting for this bias requires understanding the foreground mass distribution and calculating the probability of various magnification factors. For GN-z11 specifically, magnification bias was unlikely to be significant because the galaxy was so exceptionally bright that it would have been detected even without any magnification. Objects near the detection threshold of a survey are most affected by magnification bias, as even modest magnification can push them above detectability. GN-z11, being among the brightest galaxies at its redshift, was well above detection thresholds. This meant its discovery was not a product of magnification bias, though such bias might affect the overall census of high redshift galaxies from which GN-z11 was drawn. The broader population of bright high redshift galaxies discovered by Webb did show signs of magnification bias effects when analysed statistically. The number of bright galaxies exceeded simple extrapolations from lower redshift populations by larger factors than could be explained by magnification alone, but magnification contributed to the excess. Careful modelling that accounted for lensing effects reduced the apparent overabundance somewhat, though significant tensions with theoretical predictions remained. This suggested that while magnification explained part of the story, intrinsic evolution of galaxy properties also played an important role. The search for gravitational lensing also highlighted the importance of deep, wide-field surveys. Identifying lensed galaxies requires finding multiple images or characteristic arc shapes, which necessitates surveying areas large enough to contain rare lensing configurations. Webb's field of view is relatively small compared to wide-field survey telescopes, meaning it cannot efficiently search for lens systems. However, for objects already identified in specific deep fields, Webb's sensitivity and resolution are ideal for characterizing their properties and determining whether lensing affects the observations. Looking forward, gravitational lensing will continue to be an important consideration in studies of the early universe. As surveys push to even higher redshifts and fainter luminosities, understanding magnification effects becomes increasingly critical. Fortunately, techniques for modelling and correcting lensing effects have improved substantially, allowing researchers to account for magnification when interpreting observations. For GN-z11, the conclusion was clear. This galaxy is genuinely extreme, and its properties present real challenges to our understanding of galaxy formation. Early universe overdensity. Galaxies do not form in isolation, but within the cosmic web, the large-scale structure of dark matter filaments, sheets, nodes, and voids that pervades the universe. A galaxy's location within this structure influences its evolution by determining how much gas it can accrete, how often it experiences mergers with other galaxies, and what external forces act on it. Understanding GN-z11's environmental context became crucial for interpreting its exceptional properties. Was this galaxy forming in an overdense region where rapid growth was facilitated, or did it represent an isolated peak in an otherwise typical environment? Early observations provided limited environmental information because surveys typically focused on small fields around specific targets. The Goods North field, where GN-z11 resides, spans only a few arc-minutes on the sky, corresponding to roughly 10 million light-years at GN-z11's distance. This field of view captured GN-z11 itself, but provided little information about large-scale structure extending beyond the immediate vicinity. Determining whether GN-z11 sat in a particularly dense region required wider area surveys or targeted searches for companion galaxies at similar redshifts. Webb's Integral Field Unit observations revealed the first hints that GN-z11 might not be alone. The data showed several emission line candidates in the field around GN-z11, potential companion galaxies at similar redshifts. These candidates appeared as bright emission lines with no corresponding continuum in deep imaging, suggesting they were lower mass, actively star-forming galaxies. If confirmed at similar redshifts to GN-z11, these companions would indicate that the galaxy resided in an overdense environment, possibly a protocluster in formation. Protoclusters are the progenitors of present-day galaxy clusters, massive structures containing hundreds or thousands of galaxies. The detection of multiple potential companions was significant because it suggested GN-z11 might represent the brightest galaxy in an emerging large-scale structure. In hierarchical formation scenarios, the most massive galaxies form at the intersections of cosmic web filaments where gas and dark matter accumulate most efficiently. These locations, called nodes, become the centers of galaxy clusters over cosmic time. If GN-z11 occupied such a node at redshift 11, it would explain some of its exceptional properties. Nodes provide enhanced gas supply from multiple filaments, potentially sustaining high star formation rates. They also experience more frequent galaxy mergers, which can trigger starbursts and feed central black holes. Spectroscopic confirmation of these companion candidates remained challenging because they were faint and required long integration times with Webb spectrographs. Early observations provided tentative redshift estimates for some candidates, placing them within a few 100 million light-years of GN-z11's position. This proximity suggested they were physically associated rather than being foreground or background objects coincidentally aligned. If this association was confirmed, GN-z11 would represent one of the earliest known protoclusters, forming just 430 million years after the Big Bang. The dark matter halo mass of this potential protocluster structure was estimated using the observed number of galaxies and their luminosities. Based on relationships between galaxy luminosity and halo mass calibrated from simulations, researchers calculated that the structure might reside in a halo weighing about 30 billion solar masses. This represents a substantial overdensity compared to the average universe at that epoch, though still much less massive than present-day galaxy clusters that contain thousands of trillions of solar masses. The structure was in its infancy, just beginning to assemble the mass that would eventually form a cluster. The cosmic web structure at high redshifts differs from what we observe locally. At early times, filaments are still forming and are less well defined than in the present-day universe. Regions that will eventually become massive clusters are just beginning to stand out from the cosmic background. Simulations suggest that at redshift 10, the cosmic web consists of relatively short, thick filaments connecting small nodes, quite different from the long, thin filaments and massive clusters we see nearby. GN-z11's environment likely reflected this early stage of structure formation, with the galaxy sitting in a developing node fed by young filaments. The environmental context also affected GN-z11's role in cosmic reionization. Overdense regions reionize earlier than average because they contain more galaxies producing ionizing radiation. If GN-z11 sat in a protocluster, it likely resided within a large ionized bubble created by the combined output of multiple galaxies. This ionized bubble would facilitate the escape of Lyman alpha photons, explaining why strong Lyman alpha emission was detected despite the generally neutral intergalactic medium at this epoch. The detection of extended Lyman alpha emission around GN-z11 supported this picture, suggesting a large ionized region surrounding the galaxy. The presence of companion galaxies also raised questions about GN-z11's formation history. Had it grown primarily through mergers with smaller galaxies or through continuous gas accretion? The compact size and high stellar mass suggested that mergers played a role, as mergers efficiently funnel gas to galaxy centers and trigger intense starbursts. If GN-z11 had recently merged with one or more companions, this would explain its high star formation rate and possibly the activation of its central black hole. Mergers can drive gas into galactic nuclei, providing fuel for both star formation and black hole accretion. However, identifying specific merger signatures proved difficult. At such extreme distances, even Webb could not resolve detailed morphological features that would indicate ongoing or recent mergers. The galaxy appeared relatively smooth and compact, without obvious tidal tails or disturbed morphology. This might mean that any mergers had occurred long enough ago that the galaxy had relaxed, or that the viewing angle or resolution limitations prevented detection of merger features. High-resolution kinematic data showing complex velocity patterns provided some indirect evidence for past merger activity, but definitive confirmation remained elusive. Understanding the full environmental context of GN-z11 required mapping the large-scale structure around it. This meant surveying areas much larger than the original GOODS-North Field, searching for additional galaxies at similar redshifts. Such surveys were technically challenging because high redshift galaxies are faint and spectroscopic confirmation is time-intensive. However, the potential scientific payoff was substantial. Mapping the overdensity around GN-z11 would reveal how the environment influenced early galaxy formation and provide a test case for theoretical predictions about protocluster assembly. These observations were ongoing as Webb continued collecting data, gradually building a more complete picture of GN-z11's cosmic neighbourhood. Dust and metals in the early universe. The interstellar medium of galaxies contains not just gas, but also solid particles, dust grains composed of carbon, silicon, oxygen, and other heavy elements. These grains, typically a fraction of a micron in size, profoundly affect a galaxy's observable properties by absorbing and scattering ultraviolet and optical light, then re-emitting it at longer infrared wavelengths. In nearby star-forming galaxies, dust can obscure the majority of ultraviolet light produced by young stars, making the galaxies appear much dimmer than they actually are. Understanding the dust content of high redshift galaxies like GN-z11 is essential for correctly inferring their star formation rates and stellar masses. GN-z11 spectrum showed remarkably little evidence for dust extinction. The continuum shape, the overall brightness as a function of wavelength, appeared relatively blue and featureless, lacking the characteristic reddening that dust produces. Quantitative analysis suggested dust extinction was minimal, corresponding to less than 1/10 the dust content of typical star-forming galaxies in the present-day universe. This low dust content made sense given GN-z11's youth and low metallicity. Dust forms from heavy elements expelled by stars, so galaxies with few heavy elements naturally contain little dust. The absence of significant dust had important implications for interpreting GN-z11's properties. It meant that the observed ultraviolet luminosity directly reflected the star formation rate without requiring large corrections for dust absorption. This simplified the analysis and increased confidence in derived quantities. However, it also raised questions about exactly how much dust should be present. Even with GN-z11's subsolar metallicity, some dust should have formed from the heavy elements that supernovae had already produced. The extremely low dust content suggested either that dust formation was inefficient in the early universe or that dust was being destroyed as fast as it formed. Dust destruction can occur through multiple mechanisms. High-energy photons from young stars can shatter dust grains through a process called photodestruction. Supernova blast waves can physically destroy grains through collisions. The dense, hot environment in GN-z11's core, with intense radiation fields and frequent supernovae, would be particularly hostile to dust survival. Theoretical models suggested that in such extreme conditions, dust lifetimes might be just a few million years, short enough that steady-state dust abundances remain low despite continuous formation in supernova ejecta and stellar winds. The relationship between metallicity and dust content is not straightforward. While dust formation requires heavy elements, the efficiency of converting metals into dust depends on many factors, including temperature, density, and the specific chemical composition of the gas. Different elements condense into dust under different conditions. Carbon-based dust, such as graphite and amorphous carbon, forms from carbon-rich gas. Silicate dust forms from silicon and oxygen. Iron can exist as metallic grains or be incorporated into silicates. The relative abundances of these different dust types depend on the metallicity pattern, which in turn depends on the supernova history. GN-z11's high nitrogen abundance was particularly interesting in this context. Nitrogen is a volatile element, meaning it doesn't efficiently condense into dust under most conditions. The presence of strong nitrogen emission suggested that a significant fraction of the galaxy's heavy elements remained in the gas phase rather than being locked up in dust grains. This gaseous metal reservoir could eventually form dust if conditions changed, perhaps if the star formation rate declined, reducing the destructive radiation field, or if the gas cooled and became denser, promoting condensation. The minimal dust content also affected how we interpreted the galaxy's spectral energy distribution. The spectrum peaked in the ultraviolet, as expected for a young stellar population unobscured by dust. In dusty galaxies, the spectrum shows a second peak in the far infrared where dust re-emission dominates. GN-z11 showed no such far infrared excess, confirming the low dust content inferred from the ultraviolet spectrum. This consistency between independent measures of dust content strengthened confidence in the analysis and ruled out scenarios where dust might be present but distributed in ways that evaded detection in the ultraviolet spectrum. Looking at the broader population of high redshift galaxies, dust content showed considerable diversity. Some galaxies at similar redshifts to GN-z11 showed evidence for more substantial dust obscuration, with redder colours and far infrared emission indicating hidden star formation. This diversity suggested that dust formation and destruction rates varied significantly among early galaxies, possibly depending on factors like star formation history, metallicity pattern, or environmental conditions. GN-z11 appeared to represent the low dust end of this distribution, perhaps due to its particularly intense radiation field or specific enrichment history. The evolution of dust content over cosmic time represents an important tracer of chemical evolution. In the early universe, dust was scarce because few heavy elements existed. As stars formed and died, enriching the interstellar medium with metals, dust content gradually increased. By redshift 2 or 3, typical star-forming galaxies contain substantial amounts of dust, and by the present day, dust is ubiquitous in star-forming regions. GN-z11 captured a transitional moment in this evolution, showing that some heavy elements had formed, but dust grains remained rare. Understanding this transition helps constrain models of dust formation and provides insights into the conditions in the early universe. The detection techniques for dust at high redshift continue to improve as new facilities come online. The Atacama Large Millimeter Array can detect the cold dust that dominates the mass budget of the interstellar medium. Webb's Mid-Infrared Instrument can detect warm dust heated by star formation. Combining observations at multiple wavelengths provides a complete picture of the dust properties. For GN-z11, all available observations pointed to minimal dust, but future deeper observations at longer wavelengths might yet reveal small amounts of cold dust that current data cannot detect. Even finding such dust would not change the fundamental conclusion that GN-z11 is remarkably dust poor compared to more evolved galaxies. The Reionization connection. The epoch of Reionization marks one of the major phase transitions in cosmic history. During the first few 100 million years after the Big Bang, the universe was filled with neutral hydrogen gas that absorbed most ultraviolet light. Then, as the first galaxies formed and began producing radiation, they created bubbles of ionized gas around themselves. These bubbles gradually grew and merged until the entire universe became ionized, completing the reionization process by roughly 1 billion years after the Big Bang. GN-z11, existing at 430 million years, lived during the heart of this era and likely contributed significantly to reionization in its local environment. The evidence for GN-z11's role in reionization came from several observations. First, its prodigious ultraviolet luminosity meant it produced enormous numbers of ionizing photons. Second, the detection of Lyman alpha emission indicated that the surrounding intergalactic medium was largely ionized, allowing these photons to escape. Third, the extended Lyman alpha halo suggested a large ionized bubble surrounding the galaxy. Together, these observations painted a picture of GN-z11 as a major reionization engine, carving out an ionized region perhaps several million light-years in diameter. The physics of reionization involves a competition between ionization and recombination. Ultraviolet photons from stars and active galactic nuclei ionize hydrogen atoms by knocking electrons free. These free electrons can eventually recombine with protons to form neutral hydrogen again, emitting photons in the process. Whether a region becomes ionized depends on whether the ionization rate exceeds the recombination rate, which in turn depends on the gas density. Low-density regions ionize easily and stay ionized because recombination is slow. High-density regions require more intense radiation to ionize and can recombine quickly if the radiation source shuts off. GN-z11's ionizing photon production rate was estimated from its ultraviolet luminosity using stellar population models. The calculation required knowing the stellar masses, ages, and initial mass function to predict how many high-energy photons the stars produced. The results suggested an ionizing photon production rate of roughly 10 to the 54th photons per second. This might not sound enormous given that each hydrogen atom requires just one photon to ionize, but remembering that recombination means ionization must be maintained continuously. The rate determines how large a volume can be kept ionized. The escape fraction, the percentage of ionizing photons that escape the galaxy rather than being absorbed by internal gas, was crucial for determining GN-z11's effectiveness at reionization. Measurements suggested an escape fraction around 30%, substantially higher than typical present-day star-forming galaxies where only a few percent escape. The high escape fraction resulted from GN-z11's low dust content and possibly from channels or holes in the gas distribution created by supernova feedback. These pathways allowed photons to stream out of the galaxy into the intergalactic medium. The size of GN-z11's ionized bubble could be estimated using models that balance photon production against recombination in the surrounding gas. For the inferred ionizing luminosity and typical gas densities at this redshift, the ionized region should extend a few million light-years from the galaxy. This calculation matched the observed extent of the Lyman alpha halo, providing consistency between independent estimates. The bubble was large enough that photons traveling from GN-z11 toward Earth could escape without encountering significant neutral hydrogen, explaining why strong Lyman alpha emission was detected despite the generally neutral intergalactic medium at this epoch. If GN-z11 existed in an overdense environment with companion galaxies, the reionization picture became more complex, but also more interesting. Multiple galaxies in close proximity would produce overlapping ionized bubbles that merged into a single, large ionized region. This combined bubble would be larger and more robust than any individual galaxy could create. The photoionization from multiple sources would also maintain ionization more reliably, preventing recombination even if individual galaxies experience temporary reductions in star formation. This cooperative reionization is thought to be how the universe ultimately became fully ionized. The timing of reionization remains somewhat uncertain. Observations of the cosmic microwave background indicated that reionization was largely complete by redshift 6, about 1 billion years after the Big Bang. But when it began and how quickly it proceeded were active areas of research. GN-z11 provided a data point showing that galaxies at redshift 11 were actively ionizing their surroundings, pushing the start of reionization to at least 430 million years after the Big Bang. Whether this represented the beginning of reionization or an intermediate stage remained unclear. The morphology of reionization, whether it proceeded in large bubbles around overdensities or more uniformly across space, also remained debated. Observations of high redshift quasars showing Lyman alpha absorption features suggested that neutral hydrogen persisted in significant quantities even at redshift 6, indicating that reionization was patchy rather than uniform. GN-z11's environment, with its large ionized bubble surrounded by presumably neutral gas, exemplified this patchiness. As more galaxies formed and their bubbles expanded and merged, the neutral patches gradually shrank until the universe became fully ionized. The contribution of active galactic nuclei to reionization was another open question. Stars produce the bulk of ionizing photons in most galaxies, but AGN could dominate in systems like GN-z11 that hosted supermassive black holes. The extremely high-energy photons from AGN could penetrate deeper into neutral gas than stellar ultraviolet radiation, potentially making AGN more efficient at reionization per photon produced. However, AGN were likely rare at the highest redshifts, meaning their overall contribution might be modest, despite individual objects like GN-z11 being important locally. Understanding reionization's detailed history required observing many galaxies across a range of redshifts and measuring their ionizing photon production and escape fractions. This observational program was ongoing with Webb and ground-based telescopes. GN-z11 represented one key piece of the puzzle, showing that bright galaxies with efficient ionizing photon production existed during reionization. Whether such galaxies were common enough to explain the full reionization history remained to be determined, but GN-z11 demonstrated that at least some early galaxies were fully capable of ionizing large volumes of space. Predictions for future observations. The discoveries made about GN-z11 have opened new questions that can be addressed with future observations. As Webb continues collecting data and as next-generation facilities come online, our understanding of this remarkable galaxy and others like it will deepen. Several specific predictions and observational strategies emerge from current knowledge, pointing the way forward for high redshift galaxy studies. The goal is not just to characterize individual objects, but to understand the full population of early galaxies and how they fit into the broader picture of cosmic structure formation. One of the most pressing questions concerns GN-z11 stellar population in greater detail. Current observations provide overall properties like total stellar mass and average age, but they cannot yet distinguish between different age components or determine the detailed star formation history. Future deep spectroscopy with Webb might detect absorption lines from evolved stars, providing direct evidence for multiple generations of star formation. These observations would reveal whether GN-z11 experienced a single intense burst of star formation or sustained star formation over its entire history. The answer would constrain models of feedback and gas supply. The nature of GN-z11's central black hole remains incompletely understood. While the presence of an active galactic nucleus is established, determining the black hole's mass precisely and measuring its spin would provide crucial information about its formation and growth history. These measurements require detecting specific features in the X-ray spectrum, such as the ion emission line profile, which reflects the strong gravitational field near the black hole. Future X-ray observations with telescopes like the proposed LINX or Advanced X-ray Imaging Satellite could make these measurements, testing theories of black hole formation and growth in the early universe. The pristine gas clump discovered in GN-z11's halo demands follow-up observations. If this clump represents forming population 3 stars, detecting them directly would be transformative. Population 3 stars should produce specific spectral signatures, particularly strong helium emission without corresponding metal lines. Future Webb observations with longer integration times might detect these signatures, confirming that population 3 star formation was occurring. Alternatively, if the clump does not show population 3 signatures, understanding what it actually represents becomes important. It might be gas being accreted onto the galaxy, or material ejected by previous star formation, or something else entirely. Mapping the environment around GN-z11 more completely is a high priority. This requires wide-field spectroscopic surveys that can identify galaxies at similar redshifts across a large area. Such surveys would reveal whether GN-z11 sits in a genuine protocluster or represents a more typical environment. They would also identify potential merger partners or satellites that could affect the galaxy's evolution. Multi-object spectrographs on large ground-based telescopes, combined with Webb's deep imaging, can accomplish this mapping. The goal is to reconstruct the three-dimensional structure of the cosmic web around GN-z11. The evolution of GN-z11's descendants over cosmic time offers another avenue for understanding. While we cannot observe GN-z11 itself at later epochs, we can search for similar galaxies at intermediate redshifts and determine how their properties evolve. Do compact, star-forming galaxies like GN-z11 grow into massive ellipticals, or do they become the bulges of disk galaxies, or some other morphology? Tracing this evolutionary sequence requires identifying GN-z11 analogues at various redshifts and comparing their properties. Machine learning techniques applied to large galaxy catalogues might reveal evolutionary tracks connecting early galaxies to their present-day descendants. The role of dark matter in GN-z11's formation and evolution remains largely unexplored. Current observations constrain the total dynamical mass, but say little about how dark matter is distributed within the galaxy or how the dark matter halo influences gas accretion. Future observations could address these questions indirectly through detailed kinematic studies that map the mass distribution. Gravitational lensing studies, if GN-z11 happens to lie in front of even more distant galaxies, could directly probe the dark matter distribution. Understanding the dark matter component is essential for connecting GN-z11 to cosmological simulations and theoretical models. The dust content of GN-11, while currently low, might change as the galaxy evolves. Future observations at longer wavelengths with facilities like the Atacama Large Millimeter Array could detect cold dust that is currently below detection thresholds. Such observations would determine whether GN-z11's low observed dust content reflects a genuine absence of dust or merely the detection limits of current instruments. They would also constrain dust temperatures and masses, providing information about the dust formation rate and how efficiently heavy elements convert into solid grains. The molecular gas content of GN-z11 remains essentially unknown. While the spectrum shows ionized gas signatures, detecting the cold molecular gas that fuels star formation requires observations of molecular emission lines like carbon monoxide. These lines fall at millimeter wavelengths for GN-z11, making them accessible to ALMA. Detecting molecular gas would provide a direct measurement of the fuel available for future star formation and allow estimates of the gas consumption timescale. This would help determine whether GN-z11 can sustain its current star formation rate or will soon exhaust its gas supply. The magnetic field properties of GN-z11 represent a completely unexplored area. Magnetic fields affect how gas cools and collapses, how angular momentum is transported, and how cosmic rays propagate. Measuring magnetic fields at high redshift is technically challenging but possible through polarization observations. Dust grains align with magnetic fields, producing polarized emission that can be detected with sufficiently sensitive observations. Future facilities might make such measurements possible, revealing whether magnetic fields in the early universe were similar to those in present-day galaxies, or fundamentally different. Alternatives to standard models. The challenges that GN-z11 poses to standard galaxy formation models have prompted some researchers to consider alternative theoretical frameworks. These alternatives range from modest modifications of existing models to more radical departures from conventional wisdom. While most astronomers believe that adjustments to feedback prescriptions or initial conditions within the lambda CDM framework can ultimately explain GN-z11, exploring alternatives serves the important purpose of ensuring that we haven't overlooked other possibilities. The history of science contains many examples where anomalies that seemed merely puzzling eventually revealed fundamental new physics. One class of alternatives involves modifications to dark matter properties. Standard cold dark matter moves slowly in the early universe, allowing structure to form in a bottom-up hierarchy, where small objects form first. Warm dark matter particles move faster, suppressing small-scale structure formation. Paradoxically, this suppression might allow earlier formation of larger structures like GN-z11 because it reduces the number of small halos competing for gas. Models with warm dark matter predict fewer low-mass galaxies at high redshift, which could be tested with deep surveys. However, warm dark matter faces stringent constraints from other observations, particularly the Lyman alpha forest and the cosmic microwave background. Self-interacting dark matter represents another modification where dark matter particles can collide and scatter off each other, unlike cold dark matter, which only interacts gravitationally. These interactions would affect the density profiles of dark matter halos, potentially changing how efficiently they can capture and retain gas. Some models suggest that self-interacting dark matter could accelerate halo formation in the early universe, allowing galaxies like GN-z11 to assemble more quickly. However, like warm dark matter, self-interacting dark matter must satisfy numerous constraints, from galaxy rotation curves, cluster collisions, and structure formation simulations. Modifications to gravity itself offer more radical alternatives. While general relativity has passed every experimental test to date, some theorists propose that gravitational dynamics might differ on cosmological scales or in the early universe. Modified Newtonian dynamics, or MOND, attempts to explain galaxy rotation curves without dark matter, though extending MOND to cosmological scales has proven difficult. Other theories like FR gravity or scalar tensor theories modify general relativity in ways that could affect structure formation. Whether any of these alternatives can explain GN-z11 while satisfying all other observational constraints remains an open question. The initial conditions of the universe, determined during the inflationary epoch, might differ slightly from standard assumptions. Inflation predicts a nearly scale-invariant spectrum of density perturbations, but small deviations from perfect scale invariance are allowed. If the primordial power spectrum had more power on small scales than typically assumed, it would boost early structure formation, potentially allowing bright galaxies to form earlier. Measurements of the cosmic microwave background constrain the primordial power spectrum but with limited precision on small scales relevant to galaxy formation. GN-z11 might help constrain these small-scale properties through its implications for early structure formation. Alternative black hole formation mechanisms have received substantial attention given GN-z11's massive black hole. Standard scenarios where black holes grow from stellar remnants struggle to explain million solar mass black holes by 430 million years after the Big Bang. Direct collapse black holes, forming with initial masses of thousands to hundreds of thousands of solar masses, provide one alternative. Primordial black holes, formed in the very early universe before stars existed, offer another. Distinguishing between these scenarios requires observations of black holes at even higher redshifts and better understanding of black hole growth rates under various conditions. Modified star formation laws represent a less radical but still significant departure from standard models. The star formation rate in galaxies typically follows relationships like the Kennicutt-Schmidt law, which relates star formation rate to gas surface density. These relations were calibrated on nearby galaxies, and their applicability to the early universe remains somewhat uncertain. If star formation were more efficient at high redshift, perhaps due to higher gas temperatures, different turbulent properties, or less effective feedback, galaxies like GN-z11 could form stars more quickly than standard models predict. Testing this possibility requires measuring star formation rates and gas properties in large samples of high redshift galaxies. The role of baryonic physics in structure formation might be more important than standard models assume. Most cosmological simulations focus on dark matter dynamics because dark matter dominates the mass budget and behaves relatively simply. Ordinary matter undergoes complex processes, including cooling, heating, phase transitions, turbulence, and chemical reactions. If these processes significantly affect structure formation, perhaps through early feedback from the first stars or through large-scale flows of gas, they could change the predicted timeline for galaxy formation. Incorporating these effects into simulations remains computationally challenging, but is an active area of research. Episodic accretion represents another possibility. Standard models assume that gas accretion onto galaxies occurs relatively smoothly over time. However, simulations show that accretion can be highly time variable, with periods of rapid inflow alternating with quiescent periods. If GN-z11 were observed during a particularly intense accretion episode, its star formation rate would be temporarily elevated, potentially explaining its extreme properties without requiring fundamentally different physics. The challenge with this explanation is that it makes GN-z11's properties depend on fortunate timing, which seems somewhat unsatisfying unless similar galaxies are common. Anthropic selection effects have even been invoked, though these explanations are controversial. The anthropic principle suggests that we observe the universe having properties compatible with our existence, since we couldn't exist to observe it otherwise. Applied to GN-z11, one might argue that early massive galaxies are necessary for some aspect of later galaxy or planet formation, making their existence a prerequisite for observers. However, such arguments are difficult to formalize and harder still to test, making them unsatisfying to most physicists. They typically serve as last resorts when all conventional explanations have been exhausted. The exploration of these alternatives serves multiple purposes. First, it ensures that astronomers consider all possibilities rather than becoming locked into a single paradigm. Second, it identifies testable predictions that distinguish between different models, guiding future observations. Third, it clarifies exactly what aspects of GN-z11 are most problematic for standard models, helping focus theoretical efforts. While the lambda-CDM framework remains the most successful cosmological model overall, objects like GN-z11 push it to its limits and might eventually reveal where modifications are needed. The ultimate goal is not to overthrow successful theories, but to refine them, incorporating new physics where necessary while preserving what works. The population 3 star question. The detection of pristine gas in GN-z11's halo reignited one of astronomy's most enduring mysteries. What were the first stars like, and do any signatures of them remain visible? Population 3 stars hold a special place in cosmic history because they transformed a universe of pure hydrogen and helium into one enriched with heavy elements. Every atom of carbon in our bodies, every oxygen molecule we breathe, every silicon atom in Earth's rocks traces its ancestry back to nuclear fusion in stars. The very first stars to accomplish this feat must have been extraordinary objects, but detecting direct evidence for them has proven maddeningly difficult. Theoretical models paint population 3 stars as monsters weighing hundreds of solar masses. The reasoning stems from basic physics. Stars form when gas clouds collapse under their own gravity, and the collapse continues until pressure from heating balances gravitational compression. How much mass accumulates before this balance is reached depends on the gas's cooling efficiency. Modern gas clouds contain trace amounts of molecules like carbon monoxide and water vapor that efficiently radiate away thermal energy, allowing clouds to fragment into many small pieces that form low-mass stars. Primordial gas lacked these molecules, possessing only molecular hydrogen as a coolant. Molecular hydrogen is a much less efficient coolant than molecules containing heavy elements. It can only radiate through specific quantum mechanical transitions that occur in particular temperature ranges. As primordial gas clouds collapsed and heated, molecular hydrogen cooling could only slow the collapse, not stop it. The cloud would continue accumulating mass, growing much larger before finally forming stars. Calculations suggested typical population 3 stars weighed between 100 and 300 solar masses, true behemoths compared to typical stars forming today. Some models even predicted stars exceeding 1,000 solar masses under the most extreme conditions. Such massive stars would have been extraordinarily luminous and hot. A 200 solar mass star would shine with roughly 1 million times the Sun's luminosity and have a surface temperature exceeding 100,000 Kelvin. At these temperatures, most light emerges in the extreme ultraviolet, with energies sufficient to ionize not just hydrogen, but also helium, and even doubly ionized helium. The radiation from even a single population 3 star could ionize a bubble of gas tens or hundreds of light years across, carving out an HII region in the previously neutral primordial gas. The lifetimes of these massive stars would be remarkably short. Nuclear fusion rates scale steeply with stellar mass. More massive stars burn through their fuel much faster than low-mass stars. A 200 solar mass star would exhaust its hydrogen fuel in just 2 to 3 million years, compared to 10 billion years for a Sun-like star. After burning through hydrogen, it would quickly proceed through helium, carbon, oxygen, neon, and silicon burning, each stage proceeding faster than the last. The entire stellar evolution from birth to death might take only 3 to 5 million years, a cosmic eye blink. The death of population 3 stars would be spectacular. Stars weighing between 140 and 260 solar masses are predicted to die as pair instability supernovae. In these explosions, the core becomes so hot that gamma-ray photons spontaneously convert into electron-positron pairs. This sudden removal of radiation pressure causes catastrophic collapse, triggering a runaway thermonuclear explosion that completely obliterates the star. The energy released exceeds that of normal supernovae by factors of 10 to 100, and the explosion ejects all the star's processed material into space. No remnant black hole or neutron star remains. Pair instability supernovae would be ideal for enriching the early universe because they eject large amounts of heavy elements without leaving behind black holes that might accrete matter and bury these elements. Stars slightly less massive than the pair instability range would produce normal core collapse supernova, leaving stellar mass black holes as remnants. Stars more massive still might collapse directly to black holes without exploding at all, trapping their heavy elements inside the event horizon. The exact mass ranges for these different outcomes remain somewhat uncertain, depending on rotation rates, metallicity, which starts at 0 but increases after the first explosions, and mass loss rates. The pristine gas in GN-z11's halo, if it indeed harbours forming population 3 stars, would provide the first direct evidence of these objects. Previous searches have examined extremely metal-poor stars in the Milky Way's halo, hoping to find second-generation stars formed from gas enriched by just one or a few population 3 supernovae. Several candidates have been identified with metallicities less than 1,000th of solar, showing abundance patterns consistent with enrichment by specific types of supernovae. However, none have been found with absolute 0 metallicity that would indicate population 3 composition. These stars either don't exist in our galaxy or are too rare and faint to have been discovered yet. High redshift galaxies offer a different approach to detecting population 3 stars. Catch them while they're still forming. The challenge is that individual stars cannot be resolved at cosmological distances. Instead, astronomers must search for population 3 signatures in integrated galaxy spectra. These signatures include very strong helium emission lines, extremely hard ionizing radiation that produces high ionization states of heavy elements even when the total metallicity is low, and specific line ratios that distinguish population 3 from metal-enriched stellar populations. GN-z11's pristine gas clump showed some but not all of these signatures, making the interpretation ambiguous. The helium emission in GN-z11 was strong, but not exceptional compared to other high redshift galaxies. Population 3 stars should produce helium emission far exceeding what metal-enriched stars can create because their extreme temperatures ionize helium more efficiently. The observed helium lines in GN-z11 could potentially be explained by hot, metal-poor stars, rather than requiring truly 0 metallicity population 3 stars. Distinguishing between these scenarios required detailed spectral modelling accounting for stellar atmospheres, nebula physics, and observational uncertainties. The current data lean toward metal-poor rather than metal-free stars, but population 3 contributions couldn't be ruled out. The spatial separation of the pristine gas clump from GN-z11's main body was intriguing. If population 3 stars were forming there, it raised questions about how this pocket of gas remained unenriched while the rest of the galaxy became enriched with metals. One possibility was that the clump represented gas only recently accreted from the intergalactic medium, which had not yet mixed with the galaxy's enriched interstellar medium. Another possibility was that supernova-driven outflows had preferentially removed enriched gas from the clump's location, leaving behind primarily pristine material. Either scenario required specific geometric and dynamical conditions. The broader question of whether population 3 stars still form in the present-day universe has been debated. If the conditions for population 3 formation specifically required pristine gas with absolutely 0 heavy element content, then population 3 formation should have ended after the first supernova enriched the gas. However, if these stars could form in extremely metal-poor gas, say at metallicities below 1/1,000th of solar, then pockets of such gas might still exist, and population 3 stars might occasionally form. GN-z11's pristine gas clump, with its tentative signs of ongoing star formation, represented the best candidate yet for detecting active population 3 star formation. Future observations could clarify the situation. Deeper spectroscopy with longer integration times might detect additional emission lines that would nail down the metallicity and determine whether true population 3 stars were present. Observing the clump at multiple epochs could reveal whether the star formation signatures strengthened or changed, indicating evolution of the stellar population. Higher spatial resolution observations might resolve individual star-forming knots within the clump, providing more detailed information about what was actually forming there. Each of these observations would be challenging, but potentially transformative for our understanding of the first stars. Connecting to the cosmic microwave background. The cosmic microwave background radiation provides a snapshot of the universe at 380,000 years after the Big Bang, when atoms first formed and photons could travel freely through space. This radiation, now cooled to 2.7 Kelvin by cosmic expansion, contains information about the early universe encoded in tiny temperature fluctuations across the sky. These fluctuations reflect density variations in the primordial plasma that would eventually grow into cosmic structures. GN-z11, despite existing much later at 430 million years, connects to the CMB in several important ways that help us understand the bridge between initial conditions and galaxy formation. The CMB fluctuations have a characteristic angular scale set by the size of the universe's horizon at the time of recombination. This scale, about 1 degree on the sky, corresponds to roughly 400 million light-years at the CMB's distance. Structures on this scale in the CMB represent the largest density perturbations present at early times. These overdense regions were destined to become galaxy superclusters and large-scale structure filaments. Smaller-scale fluctuations visible in high-resolution CMB maps seeded individual galaxies and galaxy clusters. By measuring the amplitude and pattern of fluctuations at different scales, cosmologists can infer the initial conditions that led to structure formation. GN-z11 presumably formed in a region that was overdense in the CMB fluctuation map. While we cannot identify which specific CMB fluctuation evolved into GN-z11's region, the resolution and projection effects make this impossible. We can use statistical arguments. The amplitude of fluctuations at galaxy-relevant scales was approximately 1 part in 100,000. This means regions that became galaxies were only slightly denser than average initially. Over hundreds of millions of years, gravity amplified these tiny differences into the large density contrasts we observe today. GN-z11's existence implies that its region started perhaps 2 to 3 standard deviations above the mean density at recombination. The CMB also provides information about reionization through its effect on polarization. When the universe reionized, free electrons scattered CMB photons, imprinting a polarization signature. The amplitude of this signature depends on when reionization occurred and how quickly it proceeded. Measurements from the Planck satellite indicated reionization was largely complete by redshift 6, with hints suggesting it might have begun as early as redshift 10 or higher. GN-z11's existence at redshift 11, producing ionizing photons and carving out an ionized bubble, provides direct evidence for early reionization activity that contributes to the CMB polarization signal. The connection between CMB observables and galaxy formation involves complex chains of physical processes. Initial density fluctuations grew under gravity's influence, modified by dark matter properties, cosmic expansion, and baryon-photon interactions before recombination. After recombination, dark matter fluctuations grew unimpeded, while ordinary matter had to decouple from radiation pressure, cool, and eventually form molecular clouds where stars could ignite. Each step in this process is governed by physics that theoretical models must capture correctly. Testing these models requires comparing predictions for both CMB fluctuations and galaxy properties, like those of GN-z11. Recent analyses have attempted to directly connect CMB fluctuations to observed galaxies using a technique called CMB lensing. Massive structures between us and the CMB surface distort CMB photons' paths through gravitational lensing, creating correlations between CMB temperature patterns and foreground structure. By cross-correlating CMB maps with galaxy surveys, researchers can map the dark matter distribution and trace how initial fluctuations evolved into present-day structures. Extending these techniques to high redshift galaxies like GN-z11 could reveal how the earliest structures connected to primordial density patterns. The primordial power spectrum, the statistical description of density fluctuations as a function of scale, is constrained by CMB observations, but with limited precision on small scales. The CMB probe scales larger than about 10 million light-years effectively, while galaxy formation involves smaller scales down to individual dark matter halos. On these small scales, the power spectrum shape becomes uncertain, modified by processes during the inflation epoch and by subsequent evolution. GN-z11 and other early galaxies provide complementary constraints on these small scales, helping determine whether the power spectrum continues smoothly from CMB scales or shows features. Non-Gaussianity in primordial fluctuations represents another connection between the CMB and galaxy formation. Gaussian fluctuations, where the statistical properties follow a simple bell curve, are predicted by the simplest inflation models. Non-Gaussian fluctuations, showing deviations from this simple pattern, would indicate more complex physics during inflation. The CMB constrains non-Gaussianity at large scales, while galaxies probe smaller scales. If GN-z11 and similar galaxies are more numerous than expected from Gaussian fluctuations, it might indicate primordial non-Gaussianity, providing insights into the physics of the very early universe. The acoustic oscillations visible in the CMB, the regular pattern of peaks and troughs in the power spectrum, set a standard ruler for cosmological measurements. This ruler determines key cosmological parameters, including the universe's geometry, matter density, and expansion rate. These same parameters govern structure formation and determine when galaxies like GN-z11 should form. Consistency between CMB measurements and galaxy observations provides a powerful test of the cosmological model. Any tensions or discrepancies might indicate missing physics or systematic errors in measurements. The baryon density measured from the CMB affects galaxy formation in important ways. Baryons provide the material that forms stars, and their density relative to dark matter influences how efficiently gas can cool and collapse into galaxies. The CMB-derived baryon density agrees well with independent measurements from Big Bang nucleosynthesis, providing confidence in the value. Using this density in galaxy formation simulations helps predict when galaxies like GN-z11 should appear. The fact that GN-z11 seems to push the limits of these predictions suggests either measurement uncertainties or incomplete physics in simulations. Future CMB experiments with improved sensitivity and angular resolution will measure small-scale fluctuations more precisely, probing scales directly relevant to galaxy formation. These measurements, combined with large surveys of high redshift galaxies, will tighten the connection between initial conditions and observed structures. GN-z11 represents one of the earliest observable structures in this chain, making it a crucial link between the CMB's view of the infant universe and the rich tapestry of galaxies we see at later times. Understanding this link requires integrating observations across cosmic history, from the CMB through the Dark Ages and Reionization to the present day. What GN-z11 reveals about dark matter. Dark matter dominates the mass budget of the universe and provides the gravitational scaffolding upon which galaxies form, yet its nature remains mysterious. We know dark matter exists from gravitational effects on galaxy rotation, cluster dynamics, gravitational lensing, and cosmic structure formation. But we don't know what particles comprise it or how they interact except through gravity. GN-z11, by existing so early and with such remarkable properties, provides indirect constraints on dark matter that complement laboratory searches and other astrophysical observations. The most basic constraint comes from GN-z11's existence itself. For a billion solar mass stellar system to form by 430 million years after the Big Bang, the underlying dark matter halo must have collapsed and virialized even earlier, providing the gravitational potential well into which ordinary matter could fall. Simulations of cold dark matter predict that halos massive enough to host GN-z11 should be rare but not impossible at this epoch. The halo mass required was perhaps several billion to 10 billion solar masses, a significant overdensity relative to the average universe, but achievable in the lambda-CDM framework. If dark matter were warm rather than cold, meaning the particles move faster in the early universe, small-scale structure formation would be suppressed. Warm dark matter free streams out of small perturbations, erasing structure below a certain mass scale. This would delay the formation of the first halos and potentially prevent objects like GN-z11 from forming so early. The existence of GN-z11 therefore constrains how warm dark matter can be, setting a lower limit on the dark matter particle mass of a few kilo-electron volts. This astrophysical constraint complements direct detection experiments and cosmological probes like the Lyman alpha forest. Self-interacting dark matter, where dark matter particles can scatter off each other, would affect halo structure in ways that might be relevant for GN-z11. Standard cold dark matter halos have cuspy density profiles, with density rising steeply toward the center. Self-interacting dark matter can produce cores where the central density flattens. Whether this affects galaxy formation depends on the interaction cross-section and the halo mass. For GN-z11's estimated halo mass, self-interactions might be observable through their effect on rotation curves or stellar kinematics, though current measurements lack the precision to test this. The timing of halo formation depends critically on the amplitude of density fluctuations in the early universe. This amplitude is parameterized by a quantity called sigma-8, which measures the typical density contrast on 8 megaparsec scales. Higher sigma, 8 values mean stronger fluctuations and earlier structure formation. The existence of bright galaxies like GN-z11 at high redshift provides an upper limit on sigma-8, because if fluctuations were too strong, we would see many more such galaxies than observed. Current estimates from the CMB and large-scale structure give consistent sigma-8 values that are compatible with GN-z11's existence, though barely. Dark matter's lack of electromagnetic interactions affects how gas can cool and form stars. In a universe without dark matter, pressure forces from ordinary matter would prevent gravitational collapse on galaxy scales. Dark matter provides additional gravity that ordinary matter cannot resist with pressure, allowing structure to form. The efficiency of this process depends on the dark matter and ordinary matter densities. GN-z11's vigorous star formation suggests efficient gas cooling within its dark matter halo, consistent with standard cold dark matter predictions, but potentially problematic for some alternative scenarios. The dark matter distribution within GN-z11's halo affects gas dynamics in ways that might be observable. If dark matter is highly concentrated toward the center, the gravitational potential is deeper and rotation velocities are higher. If dark matter is more extended, the potential is shallower. Current kinematic measurements suggest GN-z11's dark matter halo has a concentration consistent with lambda CDM predictions for halos at this redshift, though uncertainties are large. more precise measurements of rotation curves and velocity dispersions could constrain halo profiles and test whether dark matter behaves as standard theory predicts. Substructure within dark matter halos might affect galaxy formation, particularly at early times. Simulations predict that dark matter halos contain numerous subhalos, smaller dark matter clumps orbiting within the main halo. These subhalos can host their own galaxies or exist as dark satellites. The abundance and properties of subhalos depend on dark matter physics. Too much substructure might disrupt disk formation in galaxies like GN-z11, while too little might prevent sufficient satellite galaxies from forming. Observations of GN-z11's environment and potential satellites provide constraints on substructure, though current data are insufficient for strong conclusions. The growth rate of dark matter halos affects when galaxies like GN-z11 can form. This growth rate depends on cosmological parameters, including the dark matter and dark energy densities and their evolution with time. If dark energy behaves differently than the standard cosmological constant, for instance, if it evolves with time, halo growth rates would be modified. The early appearance of massive galaxies like GN-z11 provides constraints on dark energy properties, complementing measurements from supernovae and the CMB. Any tensions between these different probes might indicate new physics in either dark matter or dark energy sectors. Primordial black holes, if they comprise a significant fraction of dark matter, could affect structure formation in distinctive ways. These black holes, formed in the very early universe before stars existed, would cluster gravitationally like particle dark matter, but with some differences. They could seed galaxy formation more efficiently than particle dark matter and might explain the early appearance of supermassive black holes like GN-z11s. However, constraints from multiple observations severely limit how much of dark matter can be primordial black holes. At most, a few percent could be in black holes of relevant masses, probably insufficient to explain GN-z11's properties unless other factors also contributed. Looking forward, observations of many galaxies like GN-z11 will provide statistical constraints on dark matter properties. The abundance of bright galaxies at high redshift depends sensitively on dark matter clustering properties and interaction strengths. Large surveys with Webb and future telescopes will measure this abundance precisely, testing whether observations match predictions from standard cold dark matter or favour modifications. GN-z11 represents the tip of the iceberg, the brightest and most extreme example of a population that holds crucial information about dark matter's nature and its role in cosmic structure formation. The evolution pathway. Understanding GN-z11's likely future evolution provides context for interpreting what we observe today. This galaxy caught our attention because of its extreme properties at early times, but those properties won't remain constant. The galaxy will continue forming stars, experiencing mergers, growing its black hole, and gradually transforming into a different type of system. Tracing this evolutionary pathway helps us understand where GN-z11 fits in the bigger picture of galaxy evolution and what kinds of present-day galaxies might be its descendants. The most straightforward evolutionary scenario has GN-z11 continuing to form stars at high rates for tens or hundreds of millions of years, gradually building up stellar mass. If the current star formation rate of 20 solar masses per year were sustained for 1 billion years, the galaxy would reach 20 billion solar masses, comparable to massive elliptical galaxies in the present-day universe. However, sustaining such high star formation rates for so long seems unlikely. Feedback processes, both from supernovae and the central AGN, should eventually regulate or quench star formation, either by heating gas to prevent collapse or by expelling it entirely from the galaxy. The timing of when star formation quenches depends on multiple factors, including gas supply, feedback efficiency, and merger history. If GN-z11 continues accreting gas from the intergalactic medium at high rates, star formation could persist longer. If the active galactic nucleus becomes more powerful and drives stronger winds, star formation might shut down relatively quickly. Observations of galaxies at somewhat lower redshifts show examples of both outcomes. Some galaxies maintain high star formation rates down to redshift 6 or 7, while others appear to have quenched by redshift 9 or 10. GN-z11 might follow either path. Mergers will likely play a crucial role in GN-z11's evolution. If the galaxy resides in an overdense region as suggested by potential companions, it should experience multiple merger events over the next billion years. Each major merger will trigger starbursts, feed the central black hole, and alter the galaxy's structure. Gas-rich mergers can sustain star formation by funneling gas to the center, while gas-poor mergers primarily rearrange existing stars without triggering new star formation. The timing and mass ratios of mergers determine the final outcome, producing anything from irregular merger remnants to smooth ellipticals. The morphological evolution of GN-z11 represents another key aspect of its future. Currently compact and dispersion-dominated, the galaxy might evolve into a massive elliptical through successive mergers, or it might settle into a rotating disk if mergers are minor and gas continues accreting. The high-velocity dispersion suggests violent processes are occurring, characteristic of galaxies that become ellipticals. However, if star formation continues and new stars form in a disk configuration, the galaxy could develop disk-like rotation. Whether GN-z11 becomes a disk or elliptical depends on its detailed merger history and angular momentum evolution. A related question is how the central black hole will evolve alongside the stellar component. If GN-z11 already hosts an actively accreting black hole, as some interpretations suggest, then black hole growth is likely to be rapid during this early phase. Periods of intense star formation and mergers naturally supply gas to the nucleus, allowing the black hole to gain mass efficiently. Over hundreds of millions of years, this could transform an initially modest black hole into one with a mass comparable to those found in the centers of massive galaxies today. The coevolution of black hole and galaxy is a defining feature of modern galaxy populations, and GN-z11 may represent an early example of that relationship being established. As the black hole grows, its influence on the host galaxy will increase. Stronger AGN feedback could heat or expel gas from the central regions, suppressing further star formation and accelerating the transition from a star-forming system to a quiescent one. This process is often invoked to explain the origin of massive elliptical galaxies in the local universe, which contain old stellar populations and little cold gas. If GN-z11 undergoes such a transition early, it could become a compact, red and dead galaxy surprisingly quickly, perhaps within 1 billion years of its initial formation. Environmental factors will also shape GN-z11's long-term evolution. If it truly lies in a dense region of the early universe, it may eventually become the central galaxy of a forming group or cluster. In that scenario, GN-z11 would grow not only through in situ star formation, but also by accreting smaller satellite galaxies. Over cosmic time, this process builds up extended stellar halos and increases galaxy size, helping to reconcile the compact nature of high redshift galaxies with the much larger sizes of present-day massive ellipticals. GN-z11 could thus be an early progenitor of a brightest cluster galaxy or a similarly dominant system. Size evolution is an important part of this picture. High redshift galaxies like GN-z11 are typically far more compact than galaxies of comparable mass today. Multiple mechanisms can drive size growth. Mergers deposit stars at larger radii, stellar winds redistribute material, and dynamical processes gradually puff up the galaxy. Even if star formation shuts down early, GN-z11's physical size is likely to increase significantly over the next several billion years. This gradual expansion is consistent with observations showing that massive galaxies at redshift 2 are already larger than their redshift 10 counterparts, yet still smaller than local ellipticals. Another uncertainty concerns the fate of GN-z11's gas reservoir. Early galaxies exist in a universe where cold gas is abundant and continuously flowing along cosmic filaments. If GN-z11 remains connected to these gas streams, it could sustain star formation longer than expected, even in the presence of feedback. Alternatively, feedback or environmental effects could sever this supply, leading to rapid gas depletion. The balance between inflows and outflows will largely determine how long GN-11 remains actively star-forming and how quickly it transitions into a more passive phase. From a population perspective, GN-z11 may represent the extreme high mass tail of early galaxy formation rather than a typical system. Its descendants would therefore be relatively rare today. Instead of becoming a Milky Way-like spiral, GN-z11 is more plausibly the ancestor of a massive elliptical galaxy or a central galaxy in a dense environment. Tracing such evolutionary links helps astronomers connect the distant universe to the structures we see around us now, turning single, high redshift detections into meaningful pieces of a much larger story. Importantly, not all evolutionary pathways are smooth or predictable. The early universe is chaotic, and small differences in initial conditions can lead to very different outcomes. A particularly energetic merger, an episode of unusually strong feedback, or changes in the surrounding environment could divert GN-z11 from an otherwise straightforward trajectory. This sensitivity makes it difficult to assign a single future to the galaxy, but it also makes systems like GN-z11 valuable laboratories for testing models of galaxy formation. Future observations will help refine these scenarios. Deeper imaging and spectroscopy can reveal whether GN-z11 has companions, how its gas is distributed, and whether its stars show signs of ordered rotation or purely random motions. Measurements of metallicity and stellar ages will constrain how long star formation has been ongoing and how efficiently gas has been converted into stars. Improved constraints on any AGN activity will clarify the role of black hole feedback at these early times. Ultimately, the evolutionary pathway of GN-z11 is best thought of not as a single line, but as a range of plausible tracks through cosmic history. What makes GN-z11 especially important is that it anchors these tracks at an extraordinarily early epoch when galaxies were first assembling their mass and structure. By understanding how such an extreme system might evolve, we gain insight into the origins of the most massive galaxies in the universe and the processes that shaped them from the very beginning. In that sense, GN-z11 is less a finished object than a snapshot of a process in motion. Its current properties tell us where it is now, but its true significance lies in what it will become. Whether it ends up as a massive elliptical, a central cluster galaxy, or something in between, GN-z11 provides a rare window into the earliest phases of galaxy evolution and the pathways that connect the infant universe to the mature cosmic structures we observe today. The limits of cosmic time. One of the most uncomfortable implications of GN-z11 is that it forces astronomers to confront the concept of cosmic time as a limiting resource. In most areas of astrophysics, time is assumed to be abundant. Galaxies have billions of years to assemble. Stars evolve over predictable lifetimes. Black holes grow gradually, regulated by feedback and fuel availability. GN-z11 breaks this assumption. It compresses processes normally spread across billions of years into a few hundred million. This compression doesn't just strain models, it exposes where time itself becomes the dominant constraint. From the moment the universe became transparent at recombination, the clock started ticking. Gravity began amplifying tiny density fluctuations, gas began falling into dark matter halos, and the first stars ignited. But those early stages were not instantaneous. Cooling, collapse, fragmentation, and feedback all take time. Every stage introduces delays. GN-z11 exists so early that even modest delays become fatal to standard explanations. There is little margin for inefficiency. Everything must happen close to the theoretical maximum speed allowed by physics. This problem becomes especially severe when considering sequential processes. Chemical enrichment cannot begin until stars form. Black hole growth cannot proceed until black hole seeds exist. Feedback cannot regulate star formation until stars and black holes are already active. Each dependency stacks on top of the previous one, creating a cascade of timing requirements. GN-z11 appears to have satisfied all of them, in order, without significant interruption. That alone makes it extraordinary. One possible interpretation is that our intuition about early cosmic time is misleading. The early universe was denser, hotter, and more dynamic than the present-day cosmos. Physical processes may simply have operated faster. Gas densities were higher, shortening collapse times. Accretion rates were larger, feeding stars and black holes more efficiently. Radiation escaped more easily due to low dust content. In this view, GN-z11 is not violating physical laws, but exploiting an environment where those laws operate near their upper limits. However, this explanation has consequences. If early cosmic conditions allowed such accelerated evolution, then many assumptions embedded in galaxy formation models must be revisited. Models calibrated on low redshift galaxies may systematically underestimate early efficiencies. Feedback prescriptions tuned to present-day environments may overestimate how effectively early galaxies self-regulated. GN-z11 suggests the early universe was not simply a scaled-down version of today, it was a qualitatively different regime. The issue of cosmic time also intersects with observational bias. We are more likely to detect galaxies like GN-z11 precisely because they are extreme. Their brightness makes them visible across vast distances. Countless less extreme galaxies likely existed alongside GN-z11, forming stars more slowly and growing more modestly, but remaining below detection thresholds. This raises a subtle question. Are we misunderstanding the early universe because we are only seeing its most extreme inhabitants? Even so, rarity does not eliminate the problem. Theoretical models predict not just averages, but distributions. GN-z11 sits at the extreme edge of those distributions, where probabilities become vanishingly small. When multiple properties, stellar mass, star formation rate, black hole mass, metallicity, are all extreme simultaneously, the statistical tension compounds. Explaining one outlier is manageable. Explaining a convergence of outliers in a single object is not. There is also the philosophical implication of temporal fine-tuning. GN-z11 appears to exist during a brief window when multiple processes align. Star formation is intense, but not yet quenched. Black hole growth is rapid, but not yet destructive. Chemical enrichment is advanced, but not complete. That window may be narrow. Catching a galaxy precisely in that phase suggests either remarkable luck or that such phases were more common than models predict. Either option carries implications for how we interpret cosmic history. Ultimately, GN-z11 challenges the idea that cosmic evolution proceeds smoothly and predictably. Instead, it hints at a universe capable of producing extreme structures very quickly under the right conditions. Time, rather than being a generous backdrop, becomes a scarce commodity. one that GN-z11 somehow managed to spend with extraordinary efficiency. GN-z11 as a stress test for cosmology. In science, the most valuable objects are not those that neatly confirm existing theories, but those that push them to their breaking point. GN-z11 functions as exactly this kind of stress test. It does not overthrow the lambda-cold dark matter model outright, but it exposes the edges where the model becomes fragile. Every major component of modern cosmology, dark matter, baryonic physics, star formation, black hole growth, must pass through GN-z11's constraints. Few emerge unscathed. At the cosmological level, GN-z11 probes the initial conditions of structure formation. It asks whether the primordial density field contained enough high-amplitude fluctuations on small scales to seed such early massive systems. If not, then either the universe's initial conditions were slightly different from standard assumptions, or the mapping from dark matter halos to visible galaxies is more efficient than believed. Both possibilities remain viable, but neither is trivial. At the astrophysical level, GN-z11 interrogates star formation physics. It challenges the idea that feedback universally suppresses efficiency. It suggests that under certain early conditions, feedback may delay regulation rather than enforce it. This has ripple effects for models of reionization, metal enrichment, and the buildup of stellar mass across cosmic time. If early galaxies were systematically more efficient than expected, then the timeline of galaxy assembly may need revision. The black hole within GN-z11 pushes even harder. Its existence so early implies that black hole seeding and growth were not marginal processes, but central features of early galaxy evolution. Black holes were not passive byproducts waiting billions of years to become relevant. They were active participants almost from the beginning. This reframes the coevolution paradigm, suggesting that galaxy black hole coupling was established far earlier than previously assumed. GN-z11 also highlights the limits of current simulations. No simulation today captures all relevant physics at sufficient resolution while spanning cosmological volumes. Choices must be made. Subgrid models stand in for unresolved processes. GN-z11 exposes where those choices matter most. It serves as a benchmark against which future simulations will be judged, not because it is typical, but because it is unforgiving. Importantly, GN-z11 does not stand alone anymore. JWST has revealed a growing population of early, bright galaxies that collectively point in the same direction. GN-z11 was the warning shot. The broader census is the sustained pressure. Together, they suggest that early galaxy formation was more rapid, more efficient, and more diverse than anticipated. Theories must now account for that reality. This does not mean cosmology is broken. It means it is incomplete. GN-z11 is not an anomaly to be dismissed. It is a constraint to be respected. The history of astrophysics is filled with such moments where unexpected observations force deeper understanding. GN-z11 appears poised to join that lineage. Early universe strain. GN-z11 matters not because it is distant, but because it is demanding. It demands that galaxies assemble faster, black holes grow earlier, and stars enrich their environments more efficiently than we thought possible. It forces us to confront the limits of our assumptions about time, efficiency, and regulation in the early universe. What makes GN-z11 especially powerful is that it does not contradict one part of theory. It pressures all of them at once. Stellar physics, black hole growth, chemical evolution, and cosmology must all align to explain its existence. That alignment is currently strained, but strain is where scientific progress often begins. GN-z11 is not a problem to be solved and set aside. It is a signpost. It points toward a universe that was capable of remarkable complexity remarkably early. Understanding how that happened will reshape not only our picture of the first galaxies, but our understanding of how cosmic structure itself came to be.